Welcome to all participants of the second ESA Ozone CCI user workshop. My name is Martin Dameris, and together with Dan Hubert and Michael van Weele, Nathalie Kalb, and Michael Eisinger, we organized this workshop. And I'm really looking forward now to two interesting, exciting sessions today and tomorrow. So it's great that so many participants are online. So I'm expecting more participants, but maybe people are coming and going, but nevertheless, it's okay. Numbers are rising still. So thanks you all for being here. So in today's and tomorrow's sessions, we will discuss ozone data products, which were developed as part of the ESA Climate Change Initiative. So it's running since 2010, and this ozone data comes from various European satellite missions since 1995. Today, the focus is on tropospheric ozone data, and tomorrow we will concentrate on stratospheric ozone data. So the program of this workshop, and as you can see from the agenda, is supported by high-ranking keynote speakers, and we are happy to have them with us, and selected scientific contributions on the use and application of these ozone data. So just to repeat, and you can see it here on the slide, the main objectives of this workshop are to bring together scientists, so involved in the generation of ozone climate data records, as well as potential users of such multi-decadal ozone time series and the broader ozone and climate community. Second, to present the state of the art of these ozone data products, in particular climate data records production. Third, the discussion results from major climate data record users. Fourth, to collect and update the user requirements, which are also important for ozone climate data records. And last but not least, to discuss the remaining challenges, and we will have time for the discussion at end of the 2 days. So I'm looking forward for our user workshop. I'm really happy that you are here, and I wish us all a very good and a successful meeting. So another note before we will start, as you can see, the presentations are recorded. So if some of you don't want this, so one of the speakers do not want it, please let us know. A last point, finally, a request to all speakers. It is important that the speaking time you can get are adhered in order to keep the program on time, which is difficult because you know that we have a hard time schedule. So thank you all for this. So, and now I will hand over to Michael van Weele, one of the co-chairs today, and he will chair the first session of today with respect to the tropospheric ozone data products.
Thank you, Martin, for this good introduction of the workshop. Second online workshop of Ozone CCI. We did it in 2021 for the first time, and so I was asked to be the chair of this first session on tropospheric ozone, and we have about 1.5 hours for this session, and afterwards there will be a break to stretch the legs. For the first presentation, the keynote is from Roland van Malderen, and I would like to introduce him as the chair of the Heue Focus Working Group for the Tropospheric Ozone Assessment Report. He works on the harmonization of ground-based data sets, which is an important task for the second phase of the TOAR project. And Roland is affiliated at the Royal Meteorological Institute in Brussels. Roland, go ahead.
Thank you, Michiel. So yeah, I will talk about the harmonization of tropospheric ozone data for TOAR II Tropospheric Ozone Assessment Report. Second phase. My name is Roland van Malderen. As said, I'm from the Royal Meteorological Institute of Belgium. And I also should acknowledge my the people who contributed to this presentation with slides and with input. So this is Owen Cooper, Daan Hubert, Arno Keppens, and Kazuyuki Miyazaki. Next slide, please. So this is the outline of the presentation. So first I will spend one slide on the importance and the formation of tropospheric ozone. Then I will more or less talk about the general background of TOAR II, TOAR I and TOAR II, the Tropospheric Ozone Assessment Report activities. But the real focus of this talk will be on the harmonization activities of tropospheric ozone within TOAR I and TOAR II. So I will talk about surface ozone data harmonization, the tropospheric ozone satellite retrieval harmonization, and the harmonization of ozone profiles from ground-based or in situ measurements. And I will end by giving an outlook. Next slide, please. So as most of you know, about 10% of atmospheric ozone resides in the troposphere. So tropospheric ozone is a strong oxidant detrimental to human health, crops, and ecosystems. Tropospheric ozone is important for tropospheric chemistry because it's a primary source of the OH radical, so-called detergent of the atmosphere. Tropospheric ozone is also an important greenhouse gas. It contributes to global warming, so it has an impact on climate, which will be assessed in TOAR. Ozone is present in the troposphere because of the exchange from the stratosphere, but it can also be formed in the troposphere by photochemical processes involving the sun and precursors like NOx, CO, and volatile organic compounds. It can also be destroyed in the troposphere photochemically, and it can also leave the troposphere due to dry deposition on the ground. Next slide, please. So I think tropospheric ozone, it should be quite obvious that it's a very important trace gas. That's why the International Global Atmospheric Chemistry, IGAC, spent an activity on it, Tropospheric Ozone Assessment Report, which has been initiated the first phase in 2014 with the mission to provide an up-to-date scientific assessment of the global distribution of and trends of tropospheric ozone all the way up from the surface up to the tropopause. And of course, one first deliverable of this tropospheric ozone assessment report, phase 1, was this assessment report, which is presented as a series of peer-reviewed papers. Next slide, please. In a special issue of the Elementa journal. So here you see the 10 TOAR assessment papers really forming the assessment report, and which can be downloaded from the special issue from Elementa. Next slide. So next deliverable was the provision of a database containing all the available surface ozone measurements worldwide. If you go to the next slide, I give you an illustration of this database. So very important about this database, the TOAR I database, is that it provided the first global scale view of all available surface ozone observations. Illustrated here is the 98th percentile of the 5-year average from 2010 till 2014. So this is really the high peak summertime values. And you can see that especially Northern America, Europe, and East Asia is nicely populated in this data set. But what is also very important with this data set is that it also provides tools to calculate ozone metrics and trends consistently for all those time series. So this database provides a kind of surface ozone data harmonization. It's really an important outcome of the first phase of TOAR I. If you go to the next slide, another important result from TOAR I is that it provided the first intercomparison of satellite ozone products. So shown here are the tropospheric ozone column mean distributions from 2010 till 2014 for 5 different satellite ozone products. And from the color plots, you can see that generally the satellite products agree quite well regarding the global tropospheric ozone hotspots. We have some hotspots over southern part of Africa, Europe, Arabia, Southeast Asia. But when we go to the next slide and we calculate the tropospheric ozone burden from those satellite ozone data sets, and we add some more, then you see that, okay, the mean values, they are quite similar among the different satellite ozone retrievals, and they're also quite similar with what IPCC models report. But the satellites really disagree regarding trends over the 2008 to 2016 decade shown there. So TOAR I identified really major discrepancies among the ozone trends reported by those different satellite products. And that's why in TOAR II there's a special focus on the retrieval of satellite ozone, and a working group which I will describe has been created. Also, seeing those tropospheric ozone trends from satellites, of course, we could also question what would be the tropospheric ozone trends from ground-based and in situ techniques. And in TOAR II, there's also a dedicated ground-based working group created, which tries to answer this question. Next slide, please. So TOAR II started in 2020, and the primary goals are, of course, to update the TOAR I database with recent ozone observations, but also by adding ozone precursor and meteorological data. Again, like TOAR I, the final product is an assessment of the tropospheric ozone distribution and trends on a regional, hemispheric, and global scales. But what is new in TOAR II is that it will also include impact studies to quantify the impact of ozone on human health, vegetation, and climate. When we go to the next slide, then we see how TOAR II is organized. So TOAR II is organized in focused working groups, and the new resource is really being developed and being done in those focused working groups. There are 16 focus working groups. You see the different teams or the different geographical focus areas mentioned here. I won't go into details, but the aim of this working groups is that they publish their findings and their results in a community special issue. If you go to the next slide, then you see there is a community special issue, which is an internal special issue hosted by Copernicus, and those 6 journals are available. So it's the aim that before the end of July this year, the focus working groups publish their findings, and this will then form the base for assessment papers. If you go to the next slide, you see again the list of the focus working groups. And here I will shortly describe current ongoing activities in 3 focus working groups. The chemical reanalysis focus working group, of course, the satellite ozone focus working group, and also the Egyptian focus working group. And I will start with the Egyptian focus working group. So if you go to the next slide. So EGIFTM stands for Harmonization and Evaluation of Ground-Based Instruments for Free Tropospheric Ozone Measurements. This focus working group, as also already mentioned, is chaired by Herman Smit and myself. And as the name describes it, the key objective is to evaluate and harmonize different free tropospheric ozone profiling datasets from well-established ground-based and in-situ measuring platforms, like the in-surface aircraft measurements from IAGOS, like measurements from ozone sondes, Brouwer-Dobson Umkehr retrievals, FTR and LiDAR retrievals. So the major deliverable to the TOAR community from this working group is quality-assessed ozone datasets with uncertainty estimates and quality flags. With the help of the chemical analysis focus working group, we also try to assess the representativeness of our data sets. And by doing the comparisons, we also want to evaluate or to identify possible instrumental drifts between our data sets. And you find the website, the link to the website on the slide as well. So if you go to the next slide, then you see that at the website you will find a description of the homogenized free tropospheric ozone profile datasets with the same template for each of those datasets, for each of those different instrumental networks. And in those descriptions, we will point to the availability. We will describe the data and data fields. The harmonization procedure will be described, and also put a focus on some data management items like flagging, certainty, traceability. So again, under this link, you will find more information. On the next slide, I will show how it looks like on the Egyptian website for the ozone sondes. So on the link you find there, you will find for the ozone sonde a map with showing the sites, the 43 sites marked by these green dots, which homogenized the ozone profile data. And also for those 43 sites, you will find the extension over time of the homogenized time series. You will also find at the website the access details. The homogenized profile data for ozone sondes are available at an FTP server. When you go to the next slide, then you will see that currently we are undertaking an estimation of the tropospheric ozone column trends based on those different homogenized data sets. So shown here are the quantile regression trends for tropospheric ozone column from the surface up to 300 hectopascal, so one common metric for the different instruments. And these are the trends shown for the 2000 till 2022 time period. Different colors denote the different trends for the different networks. And the trends are shown versus latitude on the left-hand side and versus longitude on the right-hand side. And you see some latitudinal and longitudinal variation, which we will investigate in further detail. But more or less, the trends are within ±3 ppb per decade. So this is currently ongoing research, and more details will be published in the community special issue, of course, shortly. When you go to the next slide, I also now switch from the Egyptian to the satellite ozone focus working group. And I will describe the harmonization activities ongoing at the moment in this working group. So in the satellite ozone focus working group, they include more than 20 different satellite data sets of tropospheric ozone. So the first sets are 4 data sets which give the tropospheric ozone column with the upper limit defined by a fixed pressure level varying between 100 and 300 hectopascal. When you click on the slide, you find another set of data which are also giving the tropospheric ozone column, but now with the thermal or dynamical tropopause as the upper limits. Then this is for the tropospheric ozone column. Then, of course, we also have the nadir ozone profile retrieval. These are shown in blue. These are the data sets providing those profile retrievals. We have here a flexible top level and also different prior information. So in the next 2 slides, I will first show the harmonization activities for the tropospheric column data, and then the next slides will be on the harmonization of the nadir profile data. So first, for the harmonization of tropospheric column data, the main objective here is to reduce differences related to a different top level of the tropospheric column. Here, for instance, I show for one satellite data record the dynamic linear modeling trend for the tropical mean tropospheric ozone column. So the black level shows the native top level of this satellite data records, and for reasons of harmonization, we want to add up the missing column by using the country analysis, and the different colors are then showing this entire tropospheric ozone column estimation by using different approaches, all using country analysis, but using different approaches how to fill up this missing column. And you see the variability of trends between those different approaches. When we now choose one approach for adding up the missing column, but apply it to 10 satellite data records, we get the DLM trends for the same tropical mean tropospheric ozone column field at the lower plot. But now the DLM trend is offset to the 2003 mean, so that's where the zero value at 2003 comes from. And now we see that those different data sets, although using the same harmonization approach, really show a large variation of the DLM trends over the different years, especially the blue one at the top stands out. I must say that this work is really preliminary. As you will go, as you will click, you will see it. It is done by Hubert and Arno Keppens, and it should be checked further. The next slide, you will see the harmonization of the nadir profile data within the satellite ozone focus working group. And here the main objective is to reduce differences related to different use of prior information in the satellite retrievals. So this is illustrated by showing for the EASI B August 2017 mean total tropical ozone column distribution for two different metric surfaces to the fixed upper level with a fixed pressure, and for the surface to the lobstrated tropopause. We illustrate it here, and here we use the standard products available from EASI. So we use the recommended prior and also recommended prior constraints. When we now, however, replace this recommended prior for this product with a common prior that will be applied to the different nadir profile data, this is what it looks like. At first sight, we don't see a large difference between those two tropospheric ozone column amounts. However, if we now, next to the common prior, we also apply common prior constraints, which will be applied to the different nadir profile datasets, but now illustrated for this EASI B August 2017 tropospheric ozone column amounts, then we see some differences. For instance, the lower plots, you see an increase of the tropospheric ozone column amounts, and you also see some features popping up, especially, for instance, north of Alaska. Again, this is preliminary work. If you click here, you see this is just very preliminary and should be checked, and this is really ongoing analysis. Next slide, please. So here I just want to spend one slide on the activities undertaken in the chemical reanalysis focus working group. This is chaired by Kazuyuki Miyazaki and Dylan Jones, and this is really the glue between different focus working groups. I already mentioned the use of the country analysis for the harmonization of satellite ozone retrievals, and also already mentioned, which is the third objective, the use of the chemical reanalysis models to study the spatial and temporal representativeness of the ground-based and in situ retrievals of tropospheric ozone. Two other objectives of this focus working groups is really to look at the tropospheric ozone spatial gradients and trends using chemical reanalysis, and this will be evaluated by TOAR II observations. Another objective, objective 2, is to perform to do some sensitivity analysis of the impacts of satellite and in situ observations by means of the chemical reanalysis models for capturing the distribution in the global ozone. Okay, next slide. So this is the conclusions and outlook. I think it should be clear that harmonization of datasets is really key for calculating reliable tropospheric ozone trends. I summarized 3 harmonization activities for the surface ozone, for satellite tropospheric ozone, and for ground-based and in situ tropospheric ozone profiles. The latter 2 are ongoing. The linkage between those 2 activities, those 3 activities, is done by the chemical reanalysis focus working group and also by using ozone sonars. Ozone sonars will be used to assess the success of the satellite harmonization activities. Of course, the finality of this activity is the estimation of tropospheric ozone trends, and in TOAR II also to assess the impact on climate, health, and vegetation by means of those TOAR II assessment papers. And in this context, I will end by also adding that there will be a TOAR II satellite ozone assessment paper that will be led by Dan Hubert and Kazuyuki Miyazaki. And with this, I want to thank you for attention, and I'm ready to take questions if there is time for it.
Thank you very much, Roland, for this very nice overview. We did not yet agree on how we would do this interaction. Indeed, there's a very limited time online. There's one question in the chat from Paul, and I will tell us what it is. It's how is this work coordinated with the WOUTC?
That's probably regarding the ozone sonde observations. So at the moment, yeah, the WDC and the NDAC datasets, they contain a mixture of homogenized and non-homogenized operational ozone sonde data. At the GIFTM FTP server, only homogenized data are present. Of course, this is just a temporary FTP server. It will live as long as TOAR II live, and at the end, this homogenized data set should find the way to the archives like WDC, NDAC, but probably they will be stored there as different versions of the same data sets. We still want that station PIs can provide operational corrections of a data set next to this homogenized version of the data time series that will be available in WDC, NDAC, and shadows as well.
Yes, thank you. So if there's any further interaction needed, then I would advise that you have this together with the one that asks the questions, that you keep the question sessions short. And because no one else has indicated in the chat to ask a question, maybe I should now give a chance that you indicate in the chat that you want to ask a question, and otherwise we go to the next speaker. So there's one remark. Thanks, Roland. I'm a bit worried that there are non-permanent data sets floating around that diverge from the long-term data repositories.
Yes, as I said, we will do our best to have those homogeneous data sets as soon as possible in the international archives. The problem is at the moment in the WDC and NDAC, there's no versioning possible. So if we want to store those homogeneous data sets in NDAC, the current versions are just overwritten, which is not a nice solution to station PIs who did all the best to provide an operational corrected data set. So here, but we are really making progress in this respect, and we have quite good interactions with WDC and NDAC to changes in the near future.
Okay, thanks, Roland. Yeah, in view of the time, I would like to leave the discussion here. I see hands raising. I think otherwise it might be difficult to handle such discussions, and I would prefer that you do it offline to have this further interaction on this important topic. And so I would like to proceed then to the next speaker. Thank you very much, Roland, for this. The next speaker, that's Dan Hubert, and he will give an overview of the tropospheric ozone climate data records by ESA CCI. Go ahead, Dan.
Yes, thank you. Thank you, Michiel. This is an overview of the tropospheric ozone data that are being prepared by the ESA CCI team. So this is a presentation that I will also give tomorrow, but then focusing on stratospheric and total ozone data sets. So this is work done by a large team. We are currently, our team is formed of 8 partners, and the team has been working together for almost 15 years now. We had other partners that were part of our team before, so we have a long heritage. So this is all part of ESA's climate change initiative program that started in early 2010s, that is aimed at taking maximal benefit of ESA's and ESA's third-party missions to construct long-term data records on essential climate variables. There are many domains, and ozone is one of the projects and one of the ECVs targeted by the Climate Space program. For each of these ECVs and ECV teams, the same development process is followed. So I'll quickly go through this. It's not only about data production and releasing data to people. We are really following an end-to-end approach. So there are 5 tasks in the development process. Our first task is to analyze the requirements, what the users need, what the data developers can provide, what the validation, how this is translated into validation requirements, etc. So this is also one of the topics at this workshop at the end, to have a discussion on the needs, because this is our very first step in the development process. Then we continue and develop algorithms. This has been level 2, but also especially level 3 algorithms. So single profile, single observation, single sensor, L2, or gridded multi-sensor level 3 data. It can be prototyping very new ideas, but the end idea is to evolve these prototypes into a long-term data record after further developments. This third task is then, once the algorithms are mature, to develop a system that is able to process these data. And once this full data sample is available, they are confronted to independent reference measurements. And that's task 4, validation. And finally, the last step is to actually use these ozone data sets in typical use cases by climate researchers and climate monitoring users. So all of these 5 tasks are done in a phased way. So every project phase, so we have started in 2010, but every 2-3 years there is a cycle completed like this. So this is repeatedly done every few years. So at this moment we are ending our current phase. So just after summer we will have completed another process, and in the next few years, 2024 to end of 26, we will start a new process, working on new products or improved products. All of these tasks are documented, and I'm not going to go into the details. Just want to let you know that there are a lot of documentation related to each of the tasks that can be consulted on our website. I will quickly go to the website later, but first to tell you that the target communities of this work is quite broad. So ozone products, for this particular talk, I will focus on the tropospheric ozone products. Obviously, they will feed into what Roland just presented, the tropospheric ozone assessment report by IGAC. There is also a sales activity on tropospheric ozone, where ozone CCI data is being used for intercomparisons. Connected activities are the climate services by ECMWF. So this is the climate change service that is very much linked to Ozone CCI. In fact, the intention is once a data set or algorithm is matured by the CCI team, that it is then transferred to the climate change service, C3S, so that it is extended in an operational way. So it's not for all products, but the idea is to get as much products into C3S as possible as soon as R&D on the algorithms is found, is mature. These data are also being used for comparison to CAMS, for instance. Then we are also linked to more stratospheric or UTLS communities under APARC now, usually previously SPARC. And then we also connect to the modeling, the climate modeling community, so the CCMi, CMIP, and the CMACH, which is a project by climate modelers that is part of the climate program by ESA. So all of these communities, I may have forgotten some, are our main target users. In the end, these data are being used and served to do these assessments of long-term changes related to ozone, but also climate. And that provides the entire picture. Now, I will go through each of the products that we are currently working on in CCI, tropospheric ozone products. But you can find this information on our website. So if you have any further questions after this talk, please contact either myself, I'm the science lead of this team, or go to the website that I indicated on the top right. So if you click that link, you will see this very nice page where you can find your way to our data products. This data is still outdated, but it will be updated with what is going to be released by end of this phase towards the end of this week or even tomorrow. So this will be updated. All the documents, technical documents about the algorithms, validation results, climate assessment, or user requirements can be found under the key documents link. And if you want to find out what publications the team members made using our data, or these are peer-reviewed publications describing algorithms or validation results, that's another page on this website. So now to the products. Measuring tropospheric ozone from space is really, really hard. It's just 10% of the total column. So you really have to look through 90% of ozone in order to derive the tropospheric ozone amounts. And there are a number of complementary techniques to do this. I will first talk about the convective cloud differential technique, which is a technique that is using total columns of ozone under clear sky conditions or cloudy conditions and taking the difference of these two total columns. And this gives you an idea about tropospheric columns. So we have one flagship product that is being developed by DLR using level 2 data by Bira. And this product is called GOME type tropical tropospheric ozone, which is I will shorten to GTTO, but that's what the acronym stands for. So the limitation of this technique, the technique is somewhat self-calibrating because you use the same sensor to derive total columns above cloudy scenes and clear sky scenes. So if you have any instability by taking the difference, you are less sensitive to any drift in the sensor. So that's the good point. The downside is that the technique is limited to the tropical belt. So you have data 20 south, 20 north. The other thing you have to realize is this is not a surface to tropopause column. it's limited to the altitudes where the clouds are. So the product is made to represent a column surface to about 200 or 270 hectopascals in the tropics, which corresponds to about 10 to 12 kilometers. So it's 2/3 of the tropospheric column in the tropics. So not the full column, but still we call this tropospheric column. So this is a product that has evolved, that has been part of our project before. But in the last few years, DLR worked hard on improving the product. So 2 sensors were added. The level 2 data are now in a better, or in the most recent version. The scheme to derive the tropospheric columns for individual sensors, and you see this on the right-hand side, colored by different sensors, has been improved. And then the method to actually combine the data sets, you see this on the bottom, has been improved as well. So this is a monthly mean, 1-by-1 gridded data set since 1995. Okay, this was the first technique. The second technique is to use information by different sensors. So the total columns by nadir sensors and another set of observations of vertically resolved profiles by limb sensors, or you can use a reanalysis as well. So taking the difference of a total column and a integrated stratospheric profile, you can also estimate tropospheric ozone. And this is done for 2 data sets. 2 data sets are being prepared. So this work originated, is done by FMI using data provided by Bremen and DLR and many other partners. So this work was started a few years ago, providing a data set that uses OMI and subtracts limb data to arrive at a tropospheric column. This column goes from surface to a few kilometers below the lapse rate tropopause. But as part of our current phase, a second top level was added to the product. So users can decide to use the surface to tropopause. It's a thermal tropopause, or the native product, which is surface to a few kilometers below the thermal tropopause. This is a global product. It's also 1-by-1 degree, and it's available since 2004 for the data set on the left, which is OMI limb. But what is also new in this phase is that a second source of total ozone was taken from our CCI GTO dataset. I will explain this more tomorrow, but GTO is the merged total ozone column dataset that has been used in the WMO assessments since 2014, I believe. So this is one of our key datasets that is now being used for this specific product. So that's 2 datasets coming up, providing global tropospheric columns up to the thermal tropopause. And these datasets have been compared to model simulations. This is a result by DLR using the DLR EMAC model of the trend in tropospheric columns that cover the vertical range surface to 200 hectopascals, and compare these results to the data sets that I just presented. So GTTO, which is the tropical data set, and then the global product OMI limb at the very bottom. I cropped over the tropical belt because this is where all 3 data sets provide data. The outcome of this study is that you do find some differences regionally in the trends, but overall, if you limit yourself to the same time period and you look at the broader spatial patterns, the agreement is fairly reasonable, or is at a good, the agreement is fairly good. Now off to the last technique to measure tropospheric ozone. This is a technique that relies on nadir observations, either in the visible or in the infrared. And this technique gives very high horizontal resolution, but much poorer vertical resolution than the limb profiles. So both the visible and the infrared instruments provide about 1 degree of freedom in the troposphere. So this means you have about 1 piece of actually measured information in the troposphere. So a layer or a column. So let me first go to the first data set. So this is work describing work done at RAL on the improvement of the retrieval of GOME type sensor data. So these are data sets that are available that are single profile, single sensor. So I show maps here that were presented in a recent study by Pope using 4 different GOME type sensors. And the work by the team since their previous description in 2015 by Georgina has been on improving the retrieval schemes and also using improved level 1 calibration data. 2 sensors were added and all of the data sets were extended to present times. These level 2 profiles are being prepared, are still in preparation, and data release is not foreseen at end of our current project, which is just after summer, but it will be shortly afterwards. So that's single sensor, single profile. DLR then used these level 2 profiles to combine the different sensors and to grid them. So this is a very new data product. It currently contains 5 of the GOME type sensors. So it starts in 95 with GOME. It uses a consistent level 2 algorithm by RAL. Important, the integrated profiles, because the nadir profiles is a real profile. The integrated profiles are adjusted to match with CCI's total ozone GTO dataset. And then after that, the different sensors are combined using an anomaly merging scheme. So this is an example at 20 kilometers. This is far away from the troposphere, but the idea is the same. And here I show you that the profiles consist of various levels across the entire atmosphere. There are 3 profiles levels, 3 layers residing, 2 to 3 layers residing in the troposphere for people to use for their use needs. Okay, so maybe important, this is a profile data set, but if you are interested in tropospheric ozone, you use the profiles and you extract the first few layers or the first layer as you require. Since these nadir sensors have very broad vertical resolution, if it's really important to avoid any stratospheric information, the teams recommend to use only the lowest layer in the product, which is about surface to 5.5–6 kilometers, because the second layer already contains information from the stratosphere at mid and high latitude. So if that is important, please keep this in mind. I forgot to mention, GOP stands for GOME type ozone profile. It's a bit similar naming scheme as GTTO and GTO. The final product is infrared. Again, here ULB is working on improving the level 2 retrievals. They have added a new sensor. This data set will be released and was processed using a more homogeneous level 1 calibration data and also homogeneous auxiliary data. So this is temperature and humidity information. And this is believed or shown to improve the stability of the level 2 ozone products. And ULB is also working on combining the 3 EASI sensors and provide one product to the users that is merged. So this is again profile data sets, but if you want tropospheric columns, you have to download the profiles and look at the lowest layer or layers for your needs. So I'm wrapping up. This is the table of all the products that are being considered in TOAR. And just to show you where CCI teams contributed, I'll highlight the data sets that are part of our project. I didn't have time to talk about two products made by the Bremen team. They are not formal output of the project, but they are being used for intercomparison. So Bremen, for instance, is providing an alternative CCD dataset for the team for intercomparisons, and also an alternative limb-nadir matching dataset based on OMPS measurements. You will hear from these in this workshop. If you want to download the data, either go to the CCI website. For tropospheric products, most of the datasets are accessible via CCI, via our webpage. If not, let me know about a broken link. Some of the tropospheric products are also distributed via Copernicus Climate Data Store. But most of these are currently not in the C3S service. So to end, we would be very happy if we can convince you, or we're able to convince you to work with our CCI products. Don't hesitate to contact myself as science lead or the algorithms teams directly. I haven't shown a lot of validation studies at the moment. This is because these are still much ongoing and it's too early to show any results. Please keep in mind all of the data sets that I presented will be released very soon, just after summer. If you would like to work with these a bit earlier, contact us, and perhaps it is possible to share on a case-by-case study earlier on. Also important, the climate program continues. The ozone team will continue working on algorithm improvements during 24 to 26, and that's why it's important to hear from you at the end of this day about your needs and your requirements, so we can better scope our products and our work in the coming years. And that's it. Thank you.
Thank you, Dan, for this nice overview. There was a point when you talked about the nadir limb, on what is the limb, and it has been answered in the chat that the limb stands for several limb sensors that could be used, and there's a list of instruments. What is there? And there was another question now on for the nadir products. Is there an averaging kernel if compared with models, or can you just cut off the model data at a specified level?
So the level 2 products by RAL, provided by RAL, and the level 2 products provided by ULB and LATMOS, these products contain kernels, prior information, prior constraint. All of this is contained in the product. I believe EASI, the merged EASI product, so the level 3 product, will contain a kernel, but the GOP ECV currently has no kernel. Perhaps this is something we should keep in mind to try and work on this in the next phase. Because indeed, for proper interpretation of nadir profiles, you really need to consider the averaging kernel.
Thank you. I think in view of the time, we should leave it at here. And then we go, in fact, to a model data intercomparison. So the next presentation will be by Dave Plummer, bringing chemistry, climate models, and observations together, our experience with CCMi.
Thank you very much. So yeah, I'm David Plummer, and together with Tatsuya Nagashima, we're act as the co-chairs for the Chemistry Climate Model Initiative. There is a scientific steering committee as well that helps us keep things moving along, and their names are given here. And so Dan asked me to talk a little bit about how modelers use observational data, and maybe say something thoughtful about how we could better make the two communities come together. So I'm going to attempt that. I don't know if I've really got anything revolutionary to say, but I'll show you what how we within the modeling community sort of view observations and try and use them to understand and improve our models. So if you could jump to the next slide, please. So yeah, we right now are the Chemistry Climate Model Initiative. We work to organize model intercomparison projects of chemistry climate models to improve them and also to make projections for the future. But we sort of grew out of a preceding activity called the Chemistry Climate Model Validation activity that goes back to the early 2000s. And CCMVAL, the initial work on bringing the chemistry climate modeling community together and assessing the models really kicked off at around the same time as the models themselves were under very active development, and they were first becoming capable of making, decadal and century-long simulations. So the CCMVAL activity really was there at the beginning of the dawn of these new kind of models, and they had a very keen interest in, I guess, seeing how these brand new models actually compared with observations. And I should mention, actually, both CCMVAL and CCMi have always had as a primary goal, one of our primary goals, also providing updated chemistry climate model projections for the ozone assessment, in addition to trying to advance the chemistry climate models themselves and assess them. So I'll talk a little bit about CCMVAL, in particular, some of the very first comparisons that were made back in the 2000s and sort of led up to the second phase of CCMVAL 2, and a very significant report on the evaluation of chemistry climate models that came in around 2010. And I'll come back to that report in a few minutes. Otherwise, CCMi 1 started around 2013. They proposed a new set of model experiments, and they were very actively analyzed by the international community, whoever was interested in, and a total of about nearly 40 journal articles appeared in a special issue in ACP and GMB. We started more recently a second phase of CCMi using the updated projections, notably from CMIP 6. And that phase is just beginning to hit its stride now, so I won't talk too much about it today. So the next slide, please. So sort of going back to the beginning, this is model results from the very first phase of CCMVAL. So this is a paper that was published back in 2006. And the observations are the top two left panels, and then the participating models are the other panels shown there on the right. And I apologize that it's very tiny, but I really wanted to demonstrate, to illustrate that the multi-model ensemble shows a very large spread around the different absolute amounts of total column ozone. So this is the annual cycle in total column ozone along the x-axis, January through January, and then latitude is along the y-axis there. And you can see all the models show a very similar pattern. There's low ozone in the tropics, as you'd expect. There's the mid-latitude and high latitude peak in the annual cycle in the springtime for each hemisphere. But you don't need to look too closely to convince yourself that the absolute amounts vary quite significantly across the models. And so that was the very first phase of CCMVAL. But if you skip to the next slide, please, you'll see that to some extent that range has really not changed too much. On the left-hand side is the model results from CCMi 1. So these were simulations that were done about 2015, 2016 for the tropics, so 20 south, 20 north, and there's still a 30 or 40 Dobson unit range across the different models in the absolute amount. And to really make sense of what the models are trying to tell you, you need to harmonize it to a common base period. And here is the result of that when you make all the models collapse down onto the observations around 1980. Then you can actually start to see something coherent across the models. And so I'll just skip to the next slide, please. So you really don't see too much when you try and compare directly the absolute amounts of total column ozone with observations. But trends as for observations, and modeling community is also very interested in trends, understanding how and why things are changing. And thankfully, the models do a lot better here. On the right-hand side is an analysis of these CCMi-1 simulations compared with observations. And you see the models the models are the gray line. You can see it jump around a little bit around all the observations that are plotted on that figure. But they seem to do a pretty good job of actually reproducing the trends in the observations. Somewhat as an aside here, I just want to take a moment to say that on the question of trends, and because I know there's a lot of people from the observational community here, it is an issue that's, I think, sort of growing, is when do we decide that ozone is actually recovering total column ozone? And so there's questions about internal variability in the record. How do you reduce it through processes like multiple linear regression? There's also issues of measurement uncertainty and attribution. Is the increase in total column ozone being driven in the troposphere, or is it stratosphere? So all of these issues sort of have some relevance to the ozone assessment, and is a question that may gain prominence because we are getting close to the point of having actual observed positive trends in total column ozone since the year 2000. So I just wanted to throw that out as an aside. The next figure, please. Or the next slide, please, actually. So more on trends again. In addition to total column ozone, there's significant interest in how those trends are distributed in the vertical. The models, particularly in the lower stratosphere, I like to show almost what I would call a canonical response to the acceleration of the Brewer-Dobson circulation, where ozone goes down in the tropical lower stratosphere and correspondingly increases in each of the mid-latitudes in the northern and the southern hemisphere. And so the model simulations are shown in the black line here. These are trends 2000 to 2020. This figure derives from work under the LOTUS program. And you can see the models do like to show a weak but positive trend in both the northern and southern hemisphere mid-latitudes and a corresponding decrease in the tropics, whereas the observations are much more nuanced. There's some hint, and I know it's an issue of some magnitude of decrease in particular in the northern hemisphere again. But again, there's questions about internal variability, how much confidence we can have in the measurements, and in attribution as well. These are all issues when comparing models with observations. Next slide, please. So I mentioned this briefly at the beginning that much of the work under CCMval sort of culminated in a significant report around 2010, the SPARC report on evaluation of chemistry climate models, and I just wanted to spend a little time talking about that. So if next slide, please. Try to skip through here quickly, but so yeah, the SPARC CCMval report in 2010, that was really the high water mark of the chemistry climate modeling community assessment. Again, I somewhat view it as a necessary stage in the evolution of the community, because a lot of these models were brand new, and this was really the first time they were being used for long simulations and as input for projections for, in particular, the ozone assessment. And correspondingly, there was a very comprehensive assessment. The total report is sort of around 400 pages, and it covers many different aspects of the chemistry climate models, radiation processes, dynamics. There's a chapter looking deep into the chemistry schemes that were used, as well as transport and UTLS and on and on. I think there were about 9 chapters in total looking at different aspects of chemistry climate models. And in particular, and it's something that continues to this day, there was attempts to look at process-based diagnostics. So it was not just a straight comparison between the model and the observations. You were trying to find observations that were illustrative of processes that were actually included in the model to try and improve and understand how well they're doing. So just a very quick overview of some of the comparisons that were done. The left-hand panel along the bottom is the date at which the Antarctic vortex drops breaks up, the date at which the winds transition to easterlies. Many of the models seem to hold on to the Antarctic vortex too long and have too late of a breakup. and that has a corresponding impact on the duration of the Antarctic ozone depletion. The center panel is the propagation of the water vapor tape recorder in the tropics. So again, you're trying to understand a little bit about how models are viewing the tropical upwelling, the tropical branch of the Brewer-Dobson circulation, and how quickly they are moving things up in comparison with observations. And at the right-hand panel is a look at some of the responses of the model ozone to ENSO to try and understand how well the models are representing some of the internal variability in ozone as a consequence of dynamical changes. So I think the last slide, if I'm not mistaken, please. Oh, second last, sorry. So in addition to this CCMVAL report in 2010, there has been continued work under CCMi to compare models. But it's been a little bit more of an ad hoc approach. If individual researchers have a reason and an interest, then they take the CCMi outputs and compare them against observations. For example, there's age of air, always a quantity of significant interest for modelers, compared against the available observations there. And on the right-hand side was a revisit of the tropical temperature trends in a paper by Amanda Maycock in 2018, again from the CCMi-1 simulations. So while there hasn't been a comprehensive, report on CCM since the 2010 CCMVAL-2 report, there continues to be regular comparisons against observations, but as I mentioned, on a much more ad hoc basis. So this is the last slide, I promise. If I could just jump, if I could just jump one more, please. Thank you. So conclusions, yeah. So we do see that models have significant biases in the climatological mean state. The mean state is the result of many different competing processes, and trying to figure out why these biases exist can be difficult. But the models do a lot better for trends. And there is a significant interest, of course, in trends, though, and speaking mostly for myself, working with trends can be a little bit daunting because, well, in addition to internal variability in the models and in the real world, you have to contend with observational uncertainty, something which modelers do not have a deep appreciation for. And so one place that we frequently look is a report like the Spark Data Initiative, which brings together all the available observational data sets and provides people on the outside of the observational community with some idea of how much they agree. And then there's other issues like sampling patterns that can be important when you're comparing observations with models, and is something that maybe modelers do not have a deep appreciation for. So one example of a really, I feel, a nice way in which models and observations are being brought together is happening within Lotus. They have very close connection with CCMi, and they're using the same kind of analysis on the observations as on the models. So that's a really nice example of the way in which the modeling community and observational community can meet and produce something solid. So though there hasn't been a comprehensive assessment, we continue to have ad hoc comparisons against observations motivated by individual researchers' interests, questions they might have, or other factors. And I mentioned that temperature trends paper that was motivated by the fact that some of the SSU temperature data sets had been revised since the previous comparison with models. So I get often asked of why we haven't had another comparison. And some of the things I hear in discussions with people is that models evolve slowly. So there is some concern about, how much there is new to find. And so when you get these ad hoc comparisons, there's someone who's fairly convinced that there's something new to say, but just an overall comprehensive assessment has proven to be a bit of a harder sell. But we do continue to have an interest in process-based diagnostics to understand the models and why they are giving the projections that they are. So to understand and to have increased confidence in the fact that they're doing things for the right reasons. And a lot of these process-based diagnostics do require observations about species other than just ozone. And the one that comes to mind is transport, which can be quite difficult to understand from just ozone alone. And I'll just sort of throw it out there because I know there's been a little bit of talk, and there will be further talk today on data assimilation. The community is looking at interest with these chemical data assimilations. We use unquestioningly data assimilation to compare for dynamical quantities, but we haven't quite made the jump to chemical data assimilation. So that's it for me. Thank you.
Thank you, David. I think a very interesting overview also of this time frame, a long time frame of CCMi. There's one comment from Irina on that Lotus greatly appreciates the CCMi data, and the question is, are the 2010 CCMval results still relevant to the current state of the CCMi models? So you said something about it, but maybe you can shortly comment on this question of the model evolution.
I think by and large they are. I mean, one of the things that came out of the CCMval report was that some of the models had trouble with mass conservation, had too much chlorine in the upper stratosphere, and that was a problem that was very quickly and efficiently fixed by the modeling groups when it was brought to their attention. But a lot of the other problems, for example, the structure of the Brewer-Dobson circulation or this late breakdown of the Antarctic vortex, they're just much harder problems, and so the models have evolved much more slowly. So I think there is still some significant relevance of the 2010 CCMval comparison for the models that we have today.
Okay, thank you. Looking forward to what the new phase of CCMi will bring.
Okay.
And thank you for your presentation. So then we go on to the next speaker, which is Kazuki Miyazaki. And his presentation will be on shifting patterns of global emissions and tropospheric ozone linked to human activity and natural processes derived from a decadal chemical reanalysis. Go ahead, Kazu.
Oh, thank you, Michael, and everyone. So I'm Kazu from NASA JPL. So this is a perfect order of the presentations. My topic is about the integration of the model and the satellite or any observations through the data assimilation techniques. So next, please. Okay, so as the people have discussed here or everywhere, while the NASA's or ESA's or any space agency's satellite have greatly improved our understanding of the chemical or climate system, the information that may be obtained from the combined use of those multiple satellite dataset is still limited, related to the different particle sensitivity profiles and the different overpass times, and also the mismatches in the spatial and temporal coverage, and also the chemical regime between the instrument. So data assimilation makes the best use of all available data from heterogeneous sensors and produce the chemically and dynamically consistent integrated dataset. Next, please. Yeah, thank you. So then our data assimilation system called the MOMOCHEM, that's the multi-model, multi-consistent chemical data assimilation, developed at NASA JPL, combines the multiple species information from the multiple satellite sensors for air quality and climate applications. Next, please. Then the unique characteristic of this system is the use of the multiple forecast model. So they're all chemical transport model. So this provides uncertainty informations due to model errors. Then we are currently adding the high resolution global model called the Geoschem High Performance into this MOMOCHEM framework. So this will provide the new multi-scale analysis capability. Next, please. Then our 19-year data set of emissions and concentration of many chemical species, including the ozone and the aerosol precursors, that have been used in the science applications, as well as validation of the new satellite product, including the new NASA's tropospheric ozone profile data. Then this system is also used to support the OC activities in support of mission formulation. Then I'm currently leading the IGAC TOAR II chemical reanalysis working group, working with some Copernicus people so which will be introduced later in this presentation. Next, please. Okay, so this slide shows how data assimilation constrains the tropospheric chemistry system during the decadal aura satellite era in our tropospheric chemistry reanalysis version 2, called the TCR II. So the individual assimilated data provide information on the different aspects of the tropospheric chemistry system. Then the emission data generated by the satellite data assimilation provides unique insight into the air pollution, the attributions. So this data has been widely used in attribution studies. Next, please. So in the updated reanalysis, that's the TCR version 3, we utilize more recent satellite observations, including Suomi NPP and GPSS CrIS and BIAS data, and also the multispectral retrievals from ESA and OMI developed by the NASA JPO TROPESS project, as well as the Sentinel-5P TROPOMI and others, while considering the trace gas and aerosol interactions. So this new satellite era chemical analysis framework can be used to characterize processes that form the various secondary pollutants, including ozone and aerosol, as well as their interactions and attributions. So this framework can also be used to benefit the greenhouse gas sciences through the analysis of the OH and the co-emission sources. So this is another important application of our trace gas or the aerosol, the satellite data assimilation. So click please. So the MOMOCHEM takes the full advantage of the current atmospheric composition satellite constellations for the many different applications. Next, please. Okay, so as I mentioned, the several other chemical analysis products, such as CAMS, have been made in the previous years. Then to clarify the strengths and weakness or limitation of the current reanalysis product. So we are working on the chemical reanalysis working group right now. Then the main purpose is to evaluate the current chemical reanalysis product to assess their potential for studying the ozone trend and assessing the relative importance of individual observations to improve the ozone at the surface and throughout the troposphere, and to help the design the observing system. And also, as introduced by Roland, we are working with the Heue team to evaluate representativeness of the ground-based measurement. Then more recently, under the same TOAR II framework, Dan and I are leading the satellite ozone assessment report, so which will provide the present-day maps, long-term changes, and attribution of tropospheric ozone informed by satellite observations. And we are going to evaluate agreements between the satellite records and the harmonized data product. Then we think the chemical analysis data will be the useful independent data set to evaluate or to attribute the observed ozone changes. Next, please. Okay, so unlike the many other reanalysis products that only optimize concentration field from satellite data assimilation, so in our approach, the simultaneous optimization of emissions and concentration provide the important information on global air pollutions and their impact on human health and climate. So we take the following 3 steps. The first, the global grid scale emissions of air pollutants are estimated from satellite observations. Then using that estimated emissions, the chemical transport model determines the global concentration fields that are consistent with the observations. Then finally, the obtained concentration data provides important information on the impact on human health, radiative forcing, and also atmospheric chemistry. Then this figure is an example showing the spatial pattern of NOx emission trends in the past decade, so which shows the global shift of anthropogenic emissions associated with the changes in global economic activities over the decade. Then the left figure shows the time series of the regional total emissions. So which shows a strong increase or decrease depending on the region. Then the next please. Then the reanalysis can then be used to inform the global ozone trends, which cannot be directly observed from any measurement. But the reanalysis surface ozone, informed by many different satellite observations, is in good agreement with the observed trend of the surface ozone over the limited observational site, as shown on the left. Then the click, please. Then this framework then can be used to evaluate its attribution and impact. So as an example, the lower figure shows the changes in the mortality due to changes in ozone concentration and population over the past decade. So which shows the strong increase in the number of deaths due to long-term ozone exposure for India, but it shows the significantly reduced number for the United States. So this framework, along with the attribution information, can therefore be used to support the policy decision to implement the environmental policies to mitigate the human health or climate impact. Next, please. So then we also evaluated our reanalysis against the tropospheric ozone product from the ESA multispectral retrieval developed by JPL, along with the validation with the traditional and conventional data like the ozone sonde measurement. So this figure shows the time series of the mid-tropospheric ozone between the ESA measurement and the model without any data assimilation and the chemical reanalysis from 2005 to 2022. So this the good agreement between the ESA and reanalysis demonstrates the high performance of our chemical reanalysis product and also shows the great potential of ESA data to further improve our decadal chemical reanalysis. Yeah, next please. So this figure shows the time series of the anthropogenic NOx emissions from our top-down estimations and also the CO2 emissions from bottom-up inventories for the 2005 to 2020 is shown. So the global total NOx emission is reduced by 8% in 2020, so which is comparable to the bottom-up estimate of CO2 emission reductions. Then we have worked on the COVID, the impact studies in the multiple publications, focusing on their impact on the atmospheric environment, human health, and also climate. So then the emission reductions in 2020 showed the very detailed temporal and spatial patterns. Next please, which was studied using the chemical reanalysis product. So as shown in this movie, the ozone reductions corresponding to emission decreases in each region shows the very distinct patterns. So of course, overall, the northern mid-latitude had the largest impact on ozone because of the largest NOx emission reduction. However, the emission reduction in the tropics also had a significant impact because of the stronger ozone production efficiencies, so which provides the implications into the effective policy they're making. Next, please. Then as a whole, the simulated ozone response was broad and extensive throughout the global troposphere, as shown in the left animation, and which was consistently captured by the CrIS satellite ozone data produced by JPL TROPESS product that's shown on the right. So this gives us the important implication again for policies and also the value of the current satellite constellation to inform or to detect those human-induced changes in the atmosphere. Yeah, next please. Yeah, this is my final. So this is a busy slide because I couldn't explain too many the recent activities. But I just wanted to highlight some of the recent activities we are working under this chemical reanalysis activity. So MomoChem, our system has been used in science applications and emission estimation, attribution, and evaluation and assimilation of new satellite data. Then that includes the new species measurement, such as ammonia and pan. And the two geostationary satellites are already measuring air pollutant at very high resolution. So our system will be used to uniquely relate the multi-platform observational information and comprehend the scientific understanding, including the trace gas and the aerosol synergies. Then this system has been also used to assess the observing system impact and extended to the satellite mission formulation. Then our the high-resolution system will be used to more effectively assimilate high-resolution information from the various measurements, including geo and in-situ observations. The machine learning, combining with the chemical data assimilation, is the new activity to help some downscaling or bias correction or many technical and scientific aspect. So by combining these capabilities, we aim to continue to contribute to the future missions like the ES4 and the Science to Action initiative at NASA. Okay, this is it. Thank you.
Thank you very much for your presentation. And exactly the button you didn't address, there's a question on, and that's on the aerosol synergy. And that is from Irina about mortality rates and relevance to ozone. Does the mortality rate correspond to just ozone or also to PM? And is it possible to create an air quality index from your model?
Okay, thank you for that question. The figure I showed in this presentation is about ozone only. Then that's the long-term ozone exposure. Then we have the PM data, which is constrained by many precursors and AOD measurement. So that data can be used to evaluate the PM, the exposure. Then, of course, combining the multi-species output from the chemical reanalysis, we are able to estimate AQ index data from this activity, which can be very unique and very extensive, global data, which cannot be informed by many individual observational data.
So you get an answer, and it's impressive. So thank you, Kazu, for your indeed impressive system to combine so many data in one system. I would like to proceed to the last presentation before we have a short break. This is the presentation by Victoria Sofieva, and she will inform us on the tropospheric ozone column datasets by combining nature-linked satellite measurements that have been mentioned before.
Okay, good afternoon or morning. Here's some presentation. Okay, so I will tell about two of datasets which mentioned by Dan in his presentation on tropospheric ozone column by combining nadir and LIMP satellite measurements. Next slide, please. So this is the datasets are derived by classical residual method, or a total ozone column is taken from nadir instruments. Then we create high resolution stratospheric ozone column by combining ozone profiles from several LIMP instruments, and then tropospheric ozone column is estimated as difference between total column and stratospheric ozone column. The tropospheric ozone column is evaluated on 1 by 1 degree spatial resolution on daily data, and then the data are averaged into monthly tropospheric ozone column data. Next slide, please. So for total ozone column, we use two data sets. One is OMI clear sky total ozone column, and for second, it is GTO daily total ozone column. So this is example of just for one day. For GTO, so far the data are not screened for clouds, so it can be considered in the future. And in both dataset, OMI is processed with the Godfeed algorithm. Next slide, please. So as input for stratospheric ozone column, we used a LIMP high resolution dataset. I will tell tomorrow about the details of creating this dataset. The original development was in the framework of ESA project Sunlit. And in the CCI, we improved and extended the dataset by considering more satellite instruments. Now it is data from MLS, GOMOS, MIPA, SCIAMACHY, OSIRIS, OMPS, LIMP profiler, and also we included solar occultation instruments, ACE, FTS, and CH3 on the International Space Station. So the basic idea that we created a high vertical and horizontal resolution dataset of ozone profiles. First, we homogenize data from LIMP sensors and then apply optimal interpolation, so actually it's Kriegen type of interpolation, and also use model in order to improve the data quality in the UTLS. So this is examples of original data and then interpolated field. The next slide, please. So for tropospheric ozone column datasets, we provide two columns. One, it is up to tropopause standard, and second, it is up to 3 kilometers below the tropopause. This column is if we want to separate the processes in the UTLS and the column until this level. The time coverage, it is for OMI minus LIMP is from 2004, from availability of OMI data. And for GTO, we planned data from 2002 until present. And as mentioned already, it is a monthly mean tropospheric ozone column with 1 by 1 degree horizontal resolution. For tropopause, we use thermal tropopause, but if it is not found, then we use ozonopause, or altitude where the ozone concentration gradient drops down to 3.5 Dobson unit per kilometer, if looking from the stratosphere. So, and here there's examples of tropospheric ozone column, GTO minus LIMP. This is for September 2006, or OMI minus LIMP. So these distributions look nearly identical as expected because of actually the stratospheric ozone column is the same in these two data sets. Next slide, please. We also estimated uncertainties for the tropospheric ozone column. And actually this error propagation through all steps of the deriving of the retrieval process. And here's typical uncertainties. They are larger, slightly larger for OMI minus LIMP dataset compared to GTO minus LIMP dataset. But overall, it is of order 5 Dobson unit. Slightly smaller in several locations, slightly larger in actually close to location of polar vortex or in the region of large variability. Next slide, please. So, and we compared also our tropospheric ozone columns with our other data sets, and in this comparison we actually used the upper limit as in other data sets. For example, here this comparison with OMI MLS data set for 1 month. Overall distributions are similar, but OMI minus LIMP it gives slightly lower values compared to OMI minus MLS, although here it is the data are until tropopause. And also it is observed a good agreement between OMI convective cloud differential data set and OMI minus LIMP data set. Next slide, please. We have also compared with ozone zones, and here this illustration for 2 stations in Paramaribo top and Payern, and here this time series and of OMI minus LIMP dataset, and ozone zones, either it is original, like integrated from ground to 3 kilometers below the tropopause, or we applied averaging kernel which corresponds to sensitivity of nadir instruments. So the nadir instruments then have nearly zero sensitivity close to ground, and the agreement is even better when we applied this averaging kernel. Related to seasonal cycle, it's also rather similar and nearly everywhere within uncertainty intervals. Next slide, please. So, and here there's examples of spatial and seasonal variability. So these are like location over in North America. Here this location over Asia, and we see a strong seasonal cycle. So, and all enhancement, for example, over China corresponds to big cities. And of course, shifted with the shifted out of sources of ozone. Next slide, please. As additional illustration, it is the distribution of tropospheric ozone column in January 2020 over Australia, and we see that compared to climatological mean, computed using the previous year, we have an elevated ozone level. And if considering time series analysis only for January-February months as time series, we see variations. So in the red line it is OMI minus limb with standard deviations, and in the blue GTO minus limb with standard deviations, and in 2020 it is bigger, larger values will correspond to Australian wildfires. We have also smaller enhancement in 2006, which was also the year with the pronounced wildfires in Australia. Next slide, please. And also it is as illustration, it is tropospheric ozone over China. These are only during June. So then it will be, now it will be animation. So in the left panel it will be distributions, and on the right it is time series over this smaller rectangle corresponding to maximum. So, and overall year-to-year variations are rather large, and the pattern changes, but overall this year-to-year variations are large, and therefore evaluation of trends is complicated from this time series. Next slide, please. Related to analysis of tropospheric ozone column, trends in tropospheric ozone column. So due to really large variability, so it is in the top, the figure, it is shown tropospheric ozone column anomaly in broad bands. In red tropics, blue mid-latitudes, southern hemisphere, and green mid-latitudes in northern hemisphere, we see very large variations. And also it is clear that the trends are not uniform over the whole period. And we tried different actually methods for evaluation of trends, and the overall values are similar, but the absolute values different if we use different methods for estimation of trends. Next slide, please. So here this illustration of tropospheric ozone trends estimated using multiple linear regression. On the left, it is GCO minus LIMP, and these trends are evaluated using years from 2005 to 2019. Overall, trends are not statistically significant nearly everywhere, so this is stars indicate regions where trends are not statistically significant. The only statistical significance we observe over China and also at some other locations. Trends are similar, but they are slightly different in the GCO minus LIMP compared to OMI minus LIMP. And what we also observed is negative trends over Pacific. Please click. In comparison with simulations by EMAC model, we see many similarities. And so, for example, here there's also negative trends over Pacific, but some trends are different. Next slide, please. So coming to summary, both OMI minus LIMP and GCO minus LIMP dataset will be released soon. Actually, the data are already delivered, but as Dan explained, that there's a process of validation, evaluation, and at the age of this phase of CCI, these datasets will be publicly available. So they are monthly mean tropospheric ozone column with the 1 × 1 degree resolution from 2002 for GCO minus LIMP and from 2004 for OMI minus LIMP. 2 columns up to tropopause or up to 3 kilometers below the tropopause. So what we observed that the tropospheric ozone distribution patterns similar to other datasets. And as expected, tropospheric ozone column has large seasonal spatial variations, and its evolution follows emissions. Therefore, evaluation of trends is a complicated task. Thank you.
Thank you, Victoria, for your presentation. And I think indeed it is still very complicated to compare. And so, did you have encounter issues? Or did you find things where the modelers would say, oh, we have to look into our model? Maybe it's also a question to Martin in this case, where you really learned from this data set from Victoria.
Yeah, yes, of course. So what Victoria mentioned already, there are some regions where we have a good agreement, so the patterns agree, but in other regions we do not agree, and this is something where we have to look at, let's say, for the emission inventories we are using, or we have to check for the differences between the observations and the models. But I think we are on a good way, and so such a data set is really important for the evaluation studies with respect to the CCMs.
Thank you, Martin. I think herewith we will conclude this first session of the workshop. I would like to thank all speakers again for their interesting presentations. And I would suggest that we reconvene at the top of the hour. So that is 15 minutes from now. So at the top of the hour, we continue, and then Martin will take over as chair for the second session. See you in 15 minutes.
So welcome back to our user workshop, to be on time. So we will look for session number 2, and looking forward for 5 presentations. The first one is by Natalia Kramarova from NASA Goddard Space Flight Center, and she will give a short presentation about the decade-long ozone record for Suomi NPP OMPS data. Go ahead, Natalia.
Thank you. Hello, everyone. Are you going to share my slides, or should I share my slides?
I believe you should see the slide, Natalia. I shared my screen.
No, it's not available. I do not see it.
Okay, interesting. Let me. No,
Yes,
it has a red box.
Yes.
Okay,
yes,
sorry.
Now I can see them.
Thank you.
Thank you so much. So today I will talk about ozone records from Ozone Mapping and Profiler Suite, which was launched in 2011 on board of Suomi NPP. We have records starting from April 2012, and the main question will be, can we use stratospheric ozone column from Link Profiler to continue long-term satellite record from OMI and MLS on Aura satellite. So the figure here shows you satellite record where we use stratospheric ozone column derived from MLS to calculate tropospheric ozone amount. And that record starts in 2004 and continues to present. And the main question that we address in this presentation is, can we use OMPS sensors to continue these long-term tropospheric observations? I would like to acknowledge my colleagues, first of all, Jerry Zinke, who contributed a lot in this presentation, and also Philippe Heue, Stacy Fries, and Nigel Richards. So if we go to the next slide, it shows the time series of multiple satellite ozone observations. And OMPS includes 3 sensors. One sensor is nadir mapper. It provides daily global total ozone maps, and it continues records from instruments like TOMS and OMI. Then we have nadir profilers that provides vertical ozone profiles with moderate vertical resolution, and it aims to continue BUV as BUV2 records, and it provides vertical ozone profiles and also total ozone. And then we have Link Profiler, which is supposed to continue solar occultation and link scattering methods. And right now we have 2 Link Profilers, one on the board of Suomi NPP, and there is a new Node 21 Link Profilers that started measurements last year. But in this presentation, I will focus mostly on Suomi NPP. So the next slide, recently we reprocessed data from Suomi NPP Link Profiler with a new version 2.6. It has multiple changes in both level 1 and level 2. I will not cover all these changes because I made multiple presentations on this topic. We recently submitted a paper, and preprint of this paper is available online. If we go to the next slide, it shows the altitude registration for Link Profiler. We use 350 nanometers LIMP scattered radiances to determine altitude registration for LIMP. And in version 2.5, which is shown in red, we saw time dependence and kind of upward drift in altitude registration, which affected the quality of our ozone retrievals. The ERSA's results for version 2.6 are shown in blue, and they're more stable. And this is because we updated our altitude registration. We also improved aerosol correction, and we added time-dependent wavelength correction in version 2.6. All these improved our record, and if we go to the next slide, it positively affected our ozone retrievals. Before, in version 2.5, which is the middle panel on the left, we saw substantial relative drift with respect to correlative measurements, and this slide shows the difference, the drift with respect to Aura MLS. And the drift was consistent, the pattern of this drift was consistent with possible drift in altitude registration. The drift was mostly positive above ozone peak and somewhat negative below. But now, after we reprocess with version 2.6, we can see substantial reduction in relative drift, and the bottom panel shows drift for 30-degree wide latitude beams, and you can see that version 2.6 is quite stable with respect to MLS. We also analyzed time series, and specifically at altitude where ozone is the most sensitive to altitude registration, and we found improvement. We don't see any clear linear drift anymore, and we believe that the altitude registration is as good as it could be. So if we go to the next slide, the question for this presentation was, can we use stratospheric ozone column from LP to continue MLS record? So here I'm showing time series of integrated partial columns between 12.5 and 57.5 kilometers between LP on the bottom and MLS. You can see that they correspond to each other very well in terms of latitudinal distribution and also seasonal variations. The white spots in 2022 corresponds to places where we filtered LP retrievals after the Heue eruption because of excessive stratospheric aerosol amount. So if we go to the next slide, it shows the differences between these two, on the top in Dobson units and on the bottom in percent. And you can see that there is some latitudinal patterns in biases and also some seasonal variations. But overall, we don't see any substantial drift between the two records. You can see that the biases are larger after 2022. And right now we investigate that. Our assumption that it's probably effect of Heue eruption that that negatively affected our LP ozone retrievals. But before 2022, the records are quite stable. If you press the button, it shows that the biases, the mean biases as a function of latitude, are varying between 1 to 2% or about 4%, 4 Dobson units for this stratospheric column. So the next slide shows comparisons with SOND observations. We compared the column between 12 or 18.5 kilometers up to 30 kilometers. We cut retrievals at 18 kilometers in the tropics because we don't make LP retrievals below clouds. In order to have consistent records between clouds and zones, we cut in tropics at 18.5 kilometers. So you can see the 3 latitude zones in southern hemisphere, in northern hemisphere in the middle, and in the tropics on the bottom. And you can see that LP and zones correlate very well. The panels on the right shows the differences, monthly differences with a standard deviation. What zone comparisons show that we have sort of increased differences after 2022. That kind of confirms what we saw with MLS. But overall, if you press the button, we see very similar patterns. The mean biases in both in southern mid-latitudes and in the tropics are somewhat positive, but are not statistically significant within one standard deviation. In northern hemisphere, we see almost 0 bias, but that's because the previous plot where we show comparisons with MLS shows that in some latitude beings we have positive bias, when in higher northern mid latitudes we have negative bias. So probably they just cancel out, and we see almost no biases in these latitude beings. So if we go to the next one, the main problem right now with LP retrievals is that we go down to 12.5 kilometers, and that is not sufficient to calculate stratospheric column down to the tropopause height. And it limits the spatial range for stratospheric ozone column from LP to ± 40 degrees. If we go to the next slide, the tropopause height is actually substantially above 12.5 kilometers in the tropics, but then it drops down to 10 kilometers in mid latitudes. So if we can extend LP retrievals down to 8.5 kilometers, it means that we will be able to to extend our stratospheric column down to the tropopause height. If you click yes, to this plot, it shows, so the question is, how much ozone do we have between 8.5 and 12.5 kilometers? To our surprise, we found that it's a substantial amount. It varies between 15 to 35 Dobson units, depending on latitude zone, and this is just for 1 month of October. So what you can see on this plot, you can see 2 lines for 2 climatology. One is McPeters and Labol climatology based on SOND and MLS, and another is a new climatology, Zimke et al., which is based on GMI in the troposphere and MLS in the stratosphere. And the 2 of them have bias about 5 to 7 Dobson units, which kind of increase in mid-latitudes. Then we have MLS retrievals with 2 standard deviation error bars, and then LP retrievals when we extend our retrievals down to 8.5 kilometers. And you can see biases between 2 of them as well. But what is interesting that the standard, the error bars indicate that there is a lot of variability in this column, which means that using just climatological values probably will not help to accurately determine stratospheric ozone column. We need to have retrievals. So the next question was, if you can click, yeah, so this plot, this kind of shows that everything between 30 south and 30 north is still upper tropospheric air, and we don't have to extend retrievals there, which is good because in tropics, we know that our averaging kernels are quite distorted below 18 kilometers. And so if you go to the next slide, yeah, so that the column is about 15 to 35 kilometers. So when we extend our retrievals, we want to see how good we can make our retrievals. So this plot shows retrievals at 55 south and 55 north. You can see that below 12 kilometers, which is upper red line, below that altitude, the averaging kernels becomes broader, and also the peak of the averaging kernels is shifted upward. That's especially obvious at 55 north. It's not that obvious in southern mid-latitudes. But then the vertical resolution also degrades. The vertical resolution becomes more like 3.5 kilometers. At the same time, with 3.5 kilometers vertical resolution, we will be able to resolve this layer between 8 and 12.5 kilometers. However, if we go close, so if we go to the next slide, if we go close to tropics at 35 south and north, you can see that averaging kernels degrade much faster. They become broader and the peaks are dislocated. So it means that ozone retrievals in this vertical zone are sensitive to higher altitude. The vertical resolution degrades faster. It's more like 4 or 4.5 kilometers in this vertical range. And it becomes challenging to retrieve, to accurately retrieve these columns from LP observations. So if you go to the next one, we tried to compare MLS stratospheric column and LP stratospheric column when we extended LP down to 8.5 kilometers, but only outside of tropical range. We found very good correspondence in spatial distribution of stratospheric ozone column with always positive and negative areas. And if you click, it shows the zonal mean differences between stratospheric ozone, between 2 stratospheric ozone columns. So what you can see that LP peaks are shifted somewhere northward compared to MLS, but overall agreement is zonal mean agreement is quite good. However, in some places we can see biases up to 10 Dobson units. So then we can calculate tropospheric ozone. So if you go to the next one, So we can calculate tropospheric ozone using 3 different methods. We can calculate stratospheric ozone column using Mirror 2, which is shown on the top, or we can do the same using LP and MLS. We didn't interpolate either LP or MLS retrievals for these plots, so they are very noisy because of that. But what you can notice here is that Mirror 2 underestimate wave 1 structure, and it overestimate tropospheric ozone concentration over Pacific. It kind of shows lower tropospheric ozone value, but not as low as satellite observation, LP or MLS. Between the two, LP and MLS, we can see overall good correspondence, but the largest difference that we see between two of them is in southern hemisphere, around like 40, 30 south. MLS shows substantially larger tropospheric ozone column compared to LP. And that's because, as we saw before, LP overestimate stratospheric ozone column, so it produces smaller tropospheric ozone compared to MLS. In order to make any conclusions, we need to look at larger time series, and right now we're working on this. And another question would be, if we want to have a consistent record, should we adjust stratospheric ozone column between LP and MLS to create the record? And how should we adjust these biases? These are still open questions. I don't have answers at this moment, but this is what we are doing to continue satellite tropospheric record. So the last slide, I think it's my conclusions. So if you click, yeah, this one just shows zonal mean differences. So the key points that I want to deliver is that version 2.6 record from LP is more stable and better fits for trend analysis. And we investigate if we can extend LP retrievals down to 8.5 kilometers in order to derive stratospheric ozone column. And we have to understand how good our retrievals, and for that purposes, we want to compare with sound measurements. And we also need to understand how large is the spatial and temporal variability in this lowermost stratospheric layer. So that's all I have. Thank you.
Thank you, Natalia. So there was a short statement by Larry Flynn about the current plan that is launched, JPSS4 and JPSS3 out of order. That is that JPSS4 is first. So thank you, Larry, for this statement and for this hint. I think I see no other remarks. So thank you again, Natalia. And I think we should move on to the next talk, which is by Andrea Orfanoz from Bremen. And she will give us a talk about the long-term tropospheric ozone column from SCIAMACHY and OMPS. Go ahead, please, Andrea.
Hi, a very good day. Thank you for the chance to talk to you about our latest product of SCIAMACHY and OMPS. Please, the next one. Okay, so can I move the pointer? No. It's not possible. Okay. I will drive you through this. So, sorry, now I don't.
You should see it now. Sorry, I had to switch my desktop.
Okay.
Yeah, go ahead.
Okay, thank you. We use next, to retrieve the tropospheric ozone column. We use the nadir matching technique. When basically to obtain the tropospheric ozone column, we subtract the stratospheric ozone column observed by limb measurements, yellow ones here, from total ozone column from nadir observations. What is the trick here? SCIAMACHY and OMPS, both satellite instruments, possess sensors that measure in limb and in nadir. So that allowed us to apply this technique orbit-wise without further average. So as was mentioned before, there are for different kind of data sets, there are different definition of the tropospheric ozone column of top height or top level. And for us, here in dark blue, is shown our definition, what we use as a tropopause. And it's latitudinal dependent. And for the tropic, we use the lapse rate definition of tropopause. And for latitudes above 30 degrees, the dynamical definition of tropopause, in between a weighted average. In the case, for example, in the context of the TOAR assessment, as was mentioned before, they use a fixed pressure level between 150 and I cannot see, but it doesn't matter. Here is a plot in pink. So this is important for a later point. Please, next slide. Thank you. So these are the updated data set, updated because we try to improve the method and we use the latest versions of the level 1 products. In the case, as I mentioned, but before, we use the latest version of the OMPS limb, for example, that was mentioned in the presentation before. So for the SCIAMACHY period, we use from 2002 to 2012, and for OMPS from 2012 to the present, basically. We can see the general patterns that are possible to see in other data sets, but there is a clear bias and difference between the values, considering that OMPS have lower values of tropospheric ozone than SCIAMACHY. So for please next one. So for a deeper view, we can see here 2 examples of ozone stations, Madrid in the North Hemisphere and Heue in the tropics. In red are plotted the ozone measurements, in dark blue the SCIAMACHY measurements, and in light blue the OMPS measurements, nadir MATI. So please next slide. So what is most remarkable here is that for the one less, please. Thank you. For SCIAMACHY have a larger seasonal cycle than the observed measurements in the North Hemisphere, while OMPS is much shorter. And in the tropic station, we can see the clear bias between the 2 data sets of around, can be up to 10 Dobson units. So with these 2 mixed difference between these 2 data sets, we try the merging between them. Now, next, please. And for this first attempt of merging, we use OMI MLS as a transfer function between the 2. In this upper panel here in dark blue is the SCIAMACHY time series, and OMPS is the red line for 1 grid point. This data set has been reading 5 times 5 degrees. This is just one example for 1 grid point. In green, there is OMI MLS. And in light blue, also OMI-LIN, that is also a possible candidate to be used as a transfer function to bias this. How we do for the merge? First, we need to compute the deseasonalized anomalies. That means we remove the seasonal cycle for each data set, and then we merge together here, and we use OMI MLS to reduce the bias between SCIAMACHY and OMPS. Please, next one. This is the reconstructed data set in black and OMI MLS in green. So after the bias of the data set to reconstruct this, we use the average seasonal cycle between SCIAMACHY and OMPS. What was curious for us is actually use just the seasonal cycle of OMPS, doesn't have a big impact in the reconstructed data set. Also, the overlapping time of OMI MLS with the other 2 data sets doesn't affect much the results as well. Please next. So here is a previous comparison of our reconstructed data set in green with the same two ozone stations named before that are in black, OMI-LIM in blue, OMI-MLS in red, OMPS-MERA, that is another data set, in purple. So, okay, the figure is not so clear here, but we can see that clearly the problem that we had before with the seasonal cycle of SCIAMACHY for the north has been reduced now, having a better matching seasonal cycle, and we much better the station. Although in the tropics, still we can remind this negative bias in comparison with the ozones, and actually other data sets are not able to reproduce the high values of tropospheric ozone column between 2010 and 16 that was observed in the tropic. This is just the first assessment we need, and we are working on the full validation of this data set. Please, next one. In order to make available all our data set to other users and to other definition of top levels or high levels for the column, we try 4 different methods. What we are presenting here are the maps of subcolumns between our definition of tropopause, and in this case, the definition, the top level used by TOAR for the SCIAMACHY period. And the circles in the maps correspond to the subcolumns of ozones for the same period. So first, in the left top, we try applying our algorithm directly to these top levels used by TOAR. Also, we did it scaling our data set using a seasonal climatology that is also dynamically classified. On the left bottom, a monthly climatology and a monthly dynamical climatology. It's noticeable here that these different, using climatology is just the method, produce very different results, varying along latitude as well. But if we, please next, if we take a look to these 2 specific stations that we were looking at before, for Madrid, for example, these different methods can have the cost difference of 5,000 units in between, while in the tropics, in ILO, you can see in the top right, actually these 4 methods are quite similar. So the analysis and what to use, what is better or not, is going to depend a lot of the location where we are looking at. Please, next. So in resume, what have been important and have been challenges for us, it was first the bias and the big difference in the seasonal cycle of the original data sets. Then for that was important to choose a very proper data set as a transfer function that can cover enough time for transition between these original data sets, and also that match the top high definition that we're using, the Troposphere definition. So we had to analyze, and we did analyze the influence of the choosing seasonal cycle to reconstruct the device data set. That is very important, and also have a latitudinal dependency. We are working on investigate the possible drift that we can have with other data sets, where this is available and useful to be used to analyze trends. Also, it's very important for us to remember, and for the users, that we need to be transparent about the process that we use to scale our data set when we provide this different definition to the users, because it might differ a lot, depends on what do you need as a user to use. Finally, yeah, we are discussing now, and this workshop has a lot to approach of these difficulties in harmonization and all those different data sets with these different top high levels. Thank you.
Thank you, Andrea. So I do not see any comments or in the chat. I have a question, Andrea, regarding, I think it was on chart 5. You showed the time series which are compared with the Madrid data. And it was obviously that the OMI-LIM data are looking, this I think it's this
5.
one. Yeah, because the OMI limb shows the lower values in this case here. So the blue one is showing the lowest values. And on the last chart, before you showed the conclusions, there was no differences here in the lower part with respect. So my question is, what is going on with the OMI limb data? Is there something different in these?
Okay, can you, might be a confusion here. This is the last slide is just an example for the SCIAMACHY period.
Okay.
Using our data set that is independent, is apart. So when you come back to the previous slide, please. Yeah, we keep this, but we observe that other data sets, not only OMI limbs, have this drift, this shift to lower values. And this change with latitude as well. I don't have the slide here, but when we compare all these different data sets of tropospheric column, we might have this drift, and depends if the north or south of tropics. And in the case for the north, OMI limbs looks like that. Is the data set that Victoria presented before.
Okay. Yeah, thank you, Andrea, for the clarification. Thank you.
Welcome. Thank you.
Okay, so then we should move on. So the next presentation is by Elise Pennington from NASA GPL about the quantification and evaluation of tropospheric TROPESS ozone trends and the CRLS, ARIS, and OMI satellite products. So go ahead, Elise. Thank you.
Great. Thank you for the introduction. So I will be talking about the TROPESS data products today from NASA JPL. So if we can go to the next slide, please. First, I'll introduce TROPESS. It looks like things got a little bit reformatted when I sent it over. So
I think this is a Mac Windows issue. I don't have your font, apparently. So
okay, no problem. I think
either we shift your talk to later and you give me a PDF, or we just do as what we have right now. I don't know how it will be.
Either one is fine. Most things are images, so those should probably be fine. So we can just continue for now.
Yeah.
So first I'll introduce TROPESS for a minute, and then I'm going to cover some of our early validation work as well as work on looking at long-term trends. So TROPESS is a NASA-funded project which provides a continuous record of ozone and other trace gas species retrieved from a few different satellite observations, including from instruments like CrIS, ERS, OMI, TROPOMI, and OMPS. These all use a common retrieval algorithm and estimation of errors and sensitivity, and they're all publicly available on the NASA database website. Next slide, please. So the TROPESS project provides a lot of different data sets, and what I'm showing here in bold are the data sets that are currently available, and what's shown in green are the products that I'm working with. So this includes CrIS, ERS, OMI, and then not shown at the bottom is a joint ERS OMI product. And these times, the available times vary as shown on the right. Next slide, please. So first, I'm going to talk about some of our validation work. As Roland talked about earlier, the Heue working group has been working on harmonizing the ozone sonde data. And so I've been using the ozone sonde profile data from the 43 harmonized sites shown in green from their website. Next slide, please. So here's sort of the step-by-step process of how we compare the satellite and the sonde data. So first, profiles are matched up using coincidence criteria of 300 kilometers and 9 hours. And then the satellite operator, which is the a priori profile and the averaging kernel, are applied to the sonde profiles. And that is to the full profile from the surface to the top of the atmosphere. But then we're really looking at tropospheric columns to understand tropospheric ozone. And so the way that we define a tropospheric column is by using the thermal tropopause. So that varies by time and location. And then to calculate columns, we consider temperature and water vapor profiles. And then we can also split up the tropospheric column into lower tropospheric and upper tropospheric subcolumns, split at 500 hectopascals. Next slide, please. So here's some preliminary results just from the years 2019 to 2022 for the 3 instruments shown here. These are the profiles just for the troposphere. And these traces are all showing the profiles for the sonde data once the satellite operator has been applied. And so we see that they're all showing similar shapes. The reason it's cut off at those various vertical levels is showing the difference in the tropopause height at different locations, because what's plotted here are the sonde profiles at all locations that had been matched up with satellite profiles. And then the red lines are showing the mean profiles plus or minus 1 standard deviation. And so if we go to the next slide, this is just showing the original sonde profiles overlaid with the profiles with the satellite operator applied. So just showing similar magnitudes, but now with the same vertical sensitivity as the satellite. So if we go to the next slide, we can look at the comparison between satellite and sonde profiles for, again, the same 3 instruments, AIRS, AIRS-OMI, and OMI. And so we see that the percent difference between the satellites and sonde in the troposphere tends to be positive, except for OMI, where the satellite seems to be underpredicting ozone in the upper troposphere. And the magnitude of all of these, or the mean of the magnitude, is under about 20%. And so the differences in these vertical profiles can be explained by the vertical sensitivity of each instrument. So if we go to the next slide, we have some examples here of averaging kernels for these different instruments. And so the red box is showing just the troposphere. And so we can see how CrIS and AIRS tend to have a more constant sensitivity in the lower troposphere, whereas OMI on the far right has more variability in the troposphere. So next slide, please. And here I'm just showing an example of a scatter plot showing the retrieved tropospheric ozone columns for the satellite on the y-axis and the sondes on the x-axis. And so we see fairly good agreement in the tropospheric column on the far left. But again, splitting it up into the lower troposphere in the middle and the upper troposphere on the right, we see different degrees of agreement based on the vertical sensitivity. And so all these figures have been shown for 2019 to 2022, but I'm still working on running this for all the years and doing more analyses to further investigate this vertical sensitivity, as well as if the bias has changed over time or whether it's stayed constant. So if we go to the next slide, please. So we've also been looking at long-term trends. So here what I'm showing is the long-term trend averaged monthly and averaged from 60 degrees south to 60 degrees north for the 4 satellite instruments that I talked about before. And what we see is a pretty good general agreement in terms of magnitude of these 4. And we see that CrIS, AIRS, and AIRS-OMI all demonstrate a small negative trend in ozone, whereas OMI demonstrates a slightly positive trend in ozone. And this is pretty consistent with the TOAR I assessment report, where the OMI instruments were positive and many other instruments were negative. But there's a lot of things that can explain these different trends. If we go to the next slide. One of these factors can be what time frame you choose. So if we just do a very simple test shown in the lower right figure, if we crop all of the data to only the window where all 4 data sets are available, so that's for CrIS starting in late 2015, we can see a different trend over this 5 or 6 year period, where now all the trends are negative, including OMI. So I'm looking more into what time range we choose and how the trends may be changing over time. Next slide, please. Also, of course, we can look at trends for different regions. So here I'm showing again, monthly averages, but now just for the tropics, 15 south to 15 north. And again, similar magnitudes, but different signs, again, negative for CrIS, AIRS, and AIRS-OMI, but increasing ozone from OMI. And as well, when we look at different satellite instruments, we see sort of shifting relative magnitudes between those different instruments. Next slide, please. And then similar to the validation work, also looking at subcolumns. So the upper plots are showing the upper tropospheric subcolumns, and the bottom plots are showing the lower tropospheric subcolumns. And so there's differences in trends again, but something that's interesting to know if we look at the left side, which is the average from 60 south to 60 north, we can see again how the vertical sensitivity of each instrument can impact the trends and where ozone is sort of being weighted. So for example, on the top left, we see that for AIRS-OMI, it is the largest upper tropospheric column, but if we look at the bottom, OMI has the largest lower tropospheric subcolumn. And again, this is impacted by the averaging kernels. And so if we go to the next column or next slide. So to summarize, we have been looking at the satellite SON bias. It's on the order of 10% and positive, but is impacted by the vertical sensitivity of each instrument, as are the long-term trends. We're seeing negative trends from CrIS, AIRS, and AIRS-OMI, and positive trends from OMI. But this depends on region, time period, and the subcolumn. And so as I mentioned, we're going to continue looking at the long-term bias between satellites and SONs. And then to really dive into this issue of vertical sensitivity, we're also going to be using the reanalysis data that Kazu presented on earlier, and we'll be applying the satellite operators to the reanalysis data to understand how sampling and vertical sensitivity impacts the trends and how much we can attribute the trends to each of those factors. So thank you, and happy to take any questions.
Thank you. Thank you, Elise. Questions or comments to Elise? I have a question regarding your correlation with respect to the tropospheric ozone profiles from 2019 to 2020, and there is an offset, I think, and you mentioned it already in the lower troposphere, but it is more or less an offset. It is not so. The trend is more or less let's say, robust, or not a trend, it's a correlation is robust, but there is a, yeah, please go back a little bit.
In the scatter plots.
Yeah, in the scatter plots. Yes, this one. So in the middle part, so it is interesting to see that the correlation seems to be robust, but it is an offset, which means, well, what does it mean? Is it some problem with the data itself, so the satellite data?
I don't think I have an answer for that yet.
Okay.
I still am working through the validation work right now.
Okay.
So
but it's interesting to see that on the left part and the right part of the figure. So we have, let's say, a good correlation, or more or less a good correlation. But in the middle part, which is respect to the lower troposphere, so there is this, let's say, this offset, but it's showing more or less the same in a robust correlation. Yes.
Mm-hmm. Yeah,
but the scale is different as well here. So the top leftmost and rightmost have a very large scale, and the middle one is very focused, so it may lead to the wrong conclusions.
You are right. It's a good point, Dan. Thank you. Yes. So this is misleading then, because you have a different scale. Yeah. Okay. Thanks, Dan.
Yeah. Thank you for pointing that out.
Okay. Good. There is someone who is raising his hand. I'm trying to check it. Which person is raising their hand? So please. Susan.
Hi, Elise. Nice talk. Can you go down to the one where you look at the trends and you see the difference with OMI versus the others when you're not necessarily restricting them? So what does this imply? I mean, it seems like it must imply a time-dependent drift in OMI if you accept the idea that there's 3 data sets that seem to agree and one that's really pretty clearly an outlier. And does that imply anything for stratospheric trends? What do you think?
Yeah, so we haven't really looked at stratospheric trends. I think, so 2 things that I'm going to be doing to sort of figure out why OMI may be different. One is working with the reanalysis data, like I mentioned, to see how applying the OMI operating or averaging kernel or satellite operator to the reanalysis data, how that impacts the trends seen in the reanalysis data. But another thing is I just want to dig into other variables associated with OMI. So this includes things like the sampling pattern. I need to make sure that that's been consistent over time, spatially and in terms of just like the number of points seen. Also looking at like the degrees of freedom of signal. So I don't have an exact answer yet, but definitely going to look into these other sorts of variables to make sure that they've been constant over time as well and are impacting these trends.
You might want to keep an eye on solar zenith angle too.
Yeah, that's a great point. Thank you.
Yes, thanks for the question and thanks for your answer. So then we will follow to the next talk by Klaus-Peter Heue from DLR, from the German Aerospace Center. And he will talk about the tropical tropospheric ozone absorbed from the European satellites from EIS-2 GOME from 1995 and to the Sentinel-5P TROPOMI 2024 and the resulting trends. So go ahead, Klaus.
Thank you. I just realized that my slide is less up to date than your agenda because I didn't change the title yet. Just continue. We can. Okay, here's just a quick overview about the presentation. I will focus on the CCD algorithm, and which is in the tropics only, and that is something we always have to keep in mind. I will tell you about the principle and the harmonization, and focus a bit on the trend, and also have a brief look at the last year's data, and which is not included here is some kind of a first validation steps for the data set. Okay, we can continue with the principle of the retrieval. Now, Dan already mentioned that for the CCD, we're looking at data which are big above clouds to estimate the stratospheric column, and that is then later subtracted from the total column for the cloud-free cases or almost cloud-free cases, and then we get the tropospheric column. There is one thing we have to keep in mind, that the cloud altitude varies from cloud to cloud. So we use some fixed level. In this case here, we have 200 hectopascal in the figure, but in the previous or in the operational version of S5P, we have 270 hectopascal because we have some slightly different cloud product there. And whereas for all the other sensors, we use 200 hectopascal before. So this in the end leads to two data sets. One has this 270 hectopascal using the operational S5P reprocessing data set, and the other one had the 200 hectopascal as we had before for the GOME 1 to GOME 2 data set. And here we used an internal reprocessing of the S5P data, but using the same algorithm. Some few details that we also have to keep in mind is that the stratospheric column is averaged for certain latitude bands between 70 degrees east and 170 degrees west, so going eastward in this case here. And the data are averaged 1 degree by 1 degree by 1 month, and S5P has a different resolution for the operational product, so we average them later on for the same temporal and spatial sampling. Okay, we can continue. Yeah, this is some figure for the harmonization. We compared all data to OMI, as we think that OMI is a quite stable instrument. Although, when listening to the previous talk, I'm not too sure that this actually is the case, but we're using different OMI products, so I think that should be okay. And we calculate the mean annual difference between the reference sensor, so OMI, and all the other sensors, and add that to the respective sensors, so to harmonize the data sets. There was one exception, that is GOME 1, where we only have, let's say, 1 year of overlap to SCIAMACHY for the total tropics, and therefore we only use the mean difference and do not calculate any annual cycle. If we continue, then we can see how this harmonization actually looks like. Here we see for the two data sets, 200 and 270 hectopascal, both the unharmonized data set and the harmonized data set. And we can see how all the data are more or less shifted towards the OMI in green, and afterward they agree quite well with some scatter around this data set. Also for GOME, we see that it agrees quite well, or it seems to agree quite well to the other data sets. So even though we are using a, let's say, simple harmonization in this case. Okay, if we continue, then we can look at the trends. I also looked at the trend for both data sets, 200 and 270 hectopascal, but for the beginning of the period until end of 2007, we see an increasing trend, and for both these data sets, there is a slight difference, but within the uncertainty of this trend, I think this difference or the trend agrees quite well. And for the other period, so from 2008 to 2023 or end of 2023. And we can see in the next slide, we can see a decreasing trend there. And here, oh, yeah, exactly. Here we see a quite good agreement between the two different data sets in the trend. So I think this shows this quite robust, and the differences between the two data sets are, let's say, as expected. And so from now on, I will only look at the 270 hectopascal data set. For example, we continue. I looked at the data from 2023, and I saw for January, I didn't see any, let's say, surprise, and the data agreed quite well with the climatology that is based on all the data we have since 1995. And there is, let's say, some scatter. It increases in some cases and decreases in some other cases, but it's, let's say, in the usual way. But if we go to the next slide for the November data, then we see a strong increase, especially over South America and over the Indian Ocean and Southeast Asia. And this is, let's say, was a bit surprising to see that there is such a strong increase for this year. And so I thought about what might cause this difference is, and if we continue, my first guess is that it is related to the draft that is observed over the Amazonian rainforest this year. And you see here this nice figure of the harbor in Manaus where the ships are lying on the land, on the dry. But of course, it might also be related to the El Nino effect that causes both the dry season and the increase in the ozone column. If we continue, then we can see the correlation to the ENSO index for the period from 2008 to 2023, so the last period. And we see a strong correlation over East Asia and a strong negative correlation over the Pacific, but over the Amazonian region and also over the Atlantic, there is hardly any correlation to the between the ENSO index and the ozone column, which is, let's say, in a way expected, as the ENSO index is mainly a Pacific phenomenon. Okay, that brings me to the validation, I think. Yes, for the validation, I have a slight problem that we have only monthly data. And monthly data would require about 20 sondes per month for realistic comparison. And therefore, I said, okay, for OMI, we have quite a lot of data, and we already have a 5 days average for the S5P comparison. So I extended that backward to the beginning of the OMI observation period and compared this 5 days mean to the OMI sonde. So we have the sounding day plus minus 2 days. Here's the comparison to Paramaribo, which is, let's say, Dan's favorite station when comparing S5P data to sonde data, because they will always have some difficulty during the burning seasons. And if we continue, then we can see that how it looks like for OMI. Here we have the monthly averages with the respective scatter. And we see also here in this case, during the burning season, so between July and November, we also have a slight overestimation of the OMI data compared to the sonde data. And if we continue, we can have a look at the mean data or mean comparison for every sound station. And we see it in red here. This is a Paramaribo station where we have slight overestimation. We have a very good agreement around 100° east, so in the reference region of the data set, whereas for most others we have a slight overestimation in this case. And there is one more slide on the validation, where we use the merged data set and extended the time period for the longer time period. But here we have to keep in mind that we only have monthly data and we average all data, some data we have in this month. So there is some systematic uncertainty. But overall, the agreement to the previous figure is quite good. We also see a better agreement in the reference region and a, let's say, overall positive bias for the rest of the tropics. And I think with that, I will come to my conclusion. Yeah, okay. As I said here, we have a harmonized data set for all the CCD sensors, and between 1995 and 2023, we have an increasing trend until end of 2007, and a decreasing trend from 2008. Oh, 28, that's quite ambitious. Sorry for that. A decreasing trend until the end of 2023. And we have a strong increase towards the end of last year. And yeah, that is something we would like to look into more detail. And one thing we would like to do is in the next is to update the QA indicator for the GOME and GOME 2 sensors, which currently have some problems. And one thing I realized just during this meeting here is that I should change from the shadows sonde data to the Hegev-Tom sonde. That might help for this validation, because for some cases I see some strange behavior in the shadow sonde data. And I think that's it. Thanks.
Thank you, Klaus-Peter. Any questions, comments? Klaus-Peter, I have a question regarding the increase in October, November 2023. So how robust are these signatures in comparison with the internal variability during these months? So how sure are you with respect to these differences with respect to the climatological mean?
So the standard deviation within the climatology is, I think, much lower than what we see here.
Okay.
So this was a, let's say, less than 10 Dobson units usually in the standard deviation in the. So I think it's quite robust.
Okay.
But on the other hand, I haven't seen any of my colleagues presenting a similar effect up to now. Let's say it like that. There is no one saying, "Oh, I saw that as well." So.
Okay. Thanks, Klaus-Peter. So I do not see any comments in the chat. So thank you again, Klaus-Peter. And then we will go ahead with Paul Griffiths from University of Cambridge, and he will talk about the tropospheric ozone in CMIP 6. So go ahead, Paul.
Yes, hi there, and thanks for the opportunity to present. Dan asked me to talk about the CMIP 6 process. He forgot to ask me for an abstract, and it was my fault for not checking, so I'm sorry if this catches people a little bit unaware. First of all, I should acknowledge the huge team of people that put together the CMIP 6 data sets that we used in our paper, and particularly I'd like to thank Lee Murray and Guang Zheng for their help in preparing the paper for publication. In 2019, at the AirCare MIP meeting in Princeton, we played a game of Pass the Parcel, and when the music stopped, I was left holding the ozone paper, and I'm very glad because coordinating this paper taught me a lot, and obviously I continue to learn from the business of thinking about tropospheric ozone in chemistry climate models. Next slide, please. And I think it's an interesting field because the complexity of the modelling treatment has been evolving from the 60s, where tropospheric ozone was a balance between downward transport and deposition at the surface, to a revised picture in the 70s and 80s based on in situ production in the troposphere, and then the current state of chemistry climate models is captured somewhere between the bottom two panels. A lot of processes, a lot of sophistication to some parts of the treatment of tropospheric ozone. My goal in this talk is to speak a little bit about the kind of work that goes into evaluating the models against observations when we're talking about chemistry climate models, and the business of performing multi-model assessments with the goal of quantifying model differences and the long-standing dream of understanding the cause of these differences. Ultimately, these types of papers aim to establish the performance of current chemistry climate models so as to build confidence in future climate projections. Can I have the next slide, please? So tropospheric ozone is an important greenhouse gas with a radiative forcing of about 0.4 watts per meter squared in AR5. The radiative kernel is largest in the upper troposphere, and the ozone radiative forcing is sensitive to changes in emissions, in climate, and in the sort of chemistry of the precursors. Predicting tropospheric ozone involves modelling large budget terms with strong buffering, and this means that models are useful to examine the drivers of the evolution of ozone since the pre-industrial and into the future. And on the bottom right panel, you can see a figure from Fernando Iglesias Suarez's paper from 2018, where they analyze the drivers of ozone in the future and show that climate, presumably through higher water vapor, climate change produces a small decrease in ozone through changes to the ozone budget, but we can see increases from lightning knocks and a signal from the recovery of stratospheric ozone in the 21st century. Next slide, please. So when we began to write this paper, it was important to connect with previous assessments of tropospheric ozone. This started with AR3, with a chapter on greenhouse gases and atmospheric chemistry. David Stevenson led a fantastic paper in 2006 as part of Accent, which intercompared 26 models. For AR5, Paul Young led a paper based on the ACC time slice experiments, which was able to assess 13 models. And unfortunately, pressure of time, late availability of forcing data sets, you name it, meant that for CMIP6 we had 4 models available at the time of having to draft the paper to meet the AR6 deadline, which expanded to 5 in revision. Next slide, please. So the tropospheric ozone assessment paper that we wrote for AR6, or that underpinned some parts of AR6, evaluated the models against a bunch of observations. The first set we chose was tropospheric ozone at the surface. So 5 sites with a reasonable long-term record were chosen. Models are in red, observations are in blue. You can see that the model is slightly high biased, or models, the multi-model mean is slightly high biased for almost everywhere apart from the South Pole. There are frequently strong ozone depleting events at the surface of the South Pole that we don't capture in the current generation of chemistry climate models. So this looked quite satisfactory, both in terms of absolute ozone mixing ratio and in the trend at the various stations, subject of course to some caveats when you look deeper into the data. Next slide, please. We used ozone sonde data to look at the vertical distribution of tropospheric ozone again, the multi-model mean is in orange, and the individual ozone sondators are the open circles with the error bars. And again, I would say this gives good confidence in both in terms of ozone mixing ratio as a function of altitude, and also the seasonal cycle that we see across the various latitude bins. So again, all part of the business of building confidence. Next slide, please. Use of Earth observation data is slightly more complex. This is a figure taken from our paper. The left-hand panel shows the standard deviation between the models in the tropospheric ozone column. Next column is the multi-model mean, and then OMI MLS for comparison. And then the right-hand column is the bias expressed as model minus observations. You can form your own opinions about the validity of a standard deviation with 5 models, but it aims to say something about where models agree and where they disagree in terms of their predictions. With the eye of faith, I think you can say that the distribution, the spatial distribution of ozone is pretty encouraging in the models, but it's also pretty clear that compared to OMI MLS, the models are high biased, particularly over land, and this is definitely something to think about when we go forward into thinking about how to prepare the next iteration of these types of papers. And it's been very interesting today to hear about the efforts going on to prepare harmonized data sets. So anyway, in CCMi, for the tropospheric ozone paper, we concluded that bias of the order of 25% was about average. Okay, next slide, please. We were also able to use David Tarasik's TOST data set, which is a trajectory mapped ozone sondator, basically a 5 degree by 5 degree infilled data set based on trajectory modeling. If you look in the top row, you can see that the models are significantly high biased with respect to this TOST data. Again, 25% is not uncommon. The bottom panel shows comparison with TOST and with the various data sets that were produced by that were summarized in Audrey Godel's first TOR ozone burden paper. And I show on the right the effect of different tropopause definitions on the calculated ozone burden, and you can see there's some significant variation in ozone burden based on tropopause definition. This is not unexpected. The tropopause region is a region of strong ozone gradients, and so the absolute amount of ozone in the troposphere is inevitably rather sensitive to the tropopause definition. And I should say, in CCMi-6, we only had access to a thermal tropopause diagnostic output, and so that's what was used. But you can also see if you use a chemical ozonopause approach, as was done for AR5, you get actually much less variation between the models. So there's probably more variation in model tropopause than there is in model ozone amount in the tropopause region. Next slide, please. So turning to budgets, in the last sort of few minutes of my talk, I've taken a plot here from Alex Archibald's paper that shows the net ozone production as a function of altitude. And there's also in the top right panel the zonal mean. So you can see there's strong ozone production at the surface, a kind of region of ozone destruction in the free troposphere, and then a significant amount of ozone production due to lightning knocks in the upper troposphere. Next slide, please. And so we took a look at the emissions of ozone precursors. That's the bottom left panel, the ozone budgets, which is the center panel, and a plot of the net ozone production by column in the right hand panel. And you can see that in the future, in SSP 370, which is the only SSP future climate scenario for which we had sufficient diagnostic data, so that's the only one we analysed. You can see that the emission of ozone precursors turns over around 2050. The net chemical production of ozone turns over maybe 2040. But the ozone burden carries on trucking up after 2040. And this is a consequence of the recovery of the stratospheric ozone layer and an increased amount of downward transport of ozone from the stratosphere into the troposphere, coupled with a faster Brewer-Dobson circulation. So even though ozone precursor emissions turn over, the ozone burden carries on increasing, a feature of SSP 370. And that's as far as we could get for by the AR6 deadline. Obviously, there's a glaring hole in terms of other possible climate trajectories. And maybe the next slide can speak to that. Yeah, so I'm showing on the bottom a list of data that was available nearly sort of 12 months after the final deadline. You can see that of the 5 modelling centres whose data we analysed, only a few had been able to do more than one scenario. I filled this out subsequently so we can see how the tropospheric ozone burden evolves in the different SSPs. So SSP 119 is a sustainability pathway where humanity gets its act together and emissions decrease rather sharply. SSP 370 that we focused on is a regional rivalry scenario where fossil fuel combustion continues sometime into the future. So we can begin now, somewhat after the AR6 deadline, to begin to talk about the possible impact of climate pathways on ozone burden and ozone at the surface. Next slide, please. For reasons of time, I'm going to skip over Mei-Yu and Lin's work from 2014, but it's a very nice study of the effect of climate state on the effect of the downward transport of ozone from the stratosphere. It's a fantastic paper that points out that there is an interannual variability in the ozone record at the surface, which is controlled by modes of climate variability which affect the pathways of transport. Next slide, please. And to finish with, I want to give a forward look to what I think are very exciting developments in the use of Earth observation products, which is the simultaneous application of multiple products. For instance, there was a nice paper from Kelly Wells a couple of years ago, which used the CrIS-derived isoprene measurements along with formaldehyde to infer the levels of atmospheric OH, which is an important oxidant. You could also reference Glenn Wolf's paper from 2019, which used ATOM data and formaldehyde columns to begin to talk about tropospheric oxidizing capacity. Paul Palmer had a nice paper 2 years ago about the effect of SOA on isoprene, which was backed up by a combination of model and observations. And most recently, from the Twitterverse, there's a very nice study, appears to be coming from Amir Suri, using geostationary satellite products to infer in situ ozone, column ozone production and loss at very high spatial resolution. And it'll be exciting to see how we can use this next generation of products when we perform model evaluation for CMIP 7. So anyway, with that, I'll stop and thank you for your attention.
Yeah, thank you for your presentation. Are there questions, comments, remarks? I look for the chat. There are no. Natalia, would you like to say it in your words, or should I read it? Natalia?
Oh, I'm sorry. That was comment for the previous discussion about
okay, sorry. Yeah, okay, sorry. Yes, okay.
Martin, I have a question to Paul. Paul, you said 5 models are available now. Are there more to expected in the near future?
I think
to complete your analysis,
that's a fantastic question. Owen Cooper is planning on leading an update to this paper based on CCMi 2022 experiments and CMIP 6 data, which I think will be fantastic. there's a underpinning question, which is whether more whether more climate modelling centres can afford the cost of online chemistry treatments across 250 years of transient coupled atmosphere ocean simulations. And I am wary to say that more centres will be able to do those types of experiments. So the downward trend in participating models might continue for a while, or hopefully it will at least level off. But I don't see it turning the corner.
Okay. Thanks. Paul?
Yeah, quick question, Paul. Good talk. If you go back to your last slide, you show the trend lines. That one, yeah. Yeah, the trend lines on the burden as a function of year. And the question is it methane that is mainly dominating these SSPs into the future, or is it a combination of methane and NOx? What's actually the dominant factor here? Factors?
Yeah, thank you, Paul. That's a great question. Those types of attribution experiments we did extensively for the historical period, and you can say that methane is driving half the change in the historical ozone burden. There aren't the same analogous experiments for the future climate, so actually being able to say what's driving it is difficult. But in SSP 370 and SSP 585, the methane trucks up pretty rapidly and is pretty high. And given what we know about the sensitivity of the chemistry to methane, I would say that's going to be a honking big source of tropospheric ozone. But we shouldn't discount the effect of stratospheric ozone recovery as well, I would say. But as far as we can tell, methane is a big part of the story of future ozone because it makes ozone very efficiently. Relatively.
Okay.
Thanks, Paul.
Yeah, thanks for the question. Thanks for your answer. Okay, then I think I now will hand over to Michel van Weele, who will lead the discussion about the user requirements. So go ahead, Michel.
Yeah, thank you, Martin. So we now will finish this day with a short discussion, also based on what we have heard in all the presentations today. And I have two slides to help a bit on this discussion, where we focus on tropospheric ozone today, and tomorrow we'll have a similar discussion on stratospheric ozone. And my idea would be to focus, let's say, on the experiences, what we have heard today, and on priorities. What is next? What's next to do? And that we hope to get from that the user needs, which can guide also the Ozone CCI projects for the next phase. So maybe next slide. For the tropospheric ozone products in the ESA CCI, but we also saw the products from overseas, from NASA. You can use either one or more satellite instruments, and we have seen different products. We have the infrared-based columns. We have the nadir-based UV-vis partial columns from sounders. We have the CCD technique for tropical tropospheric columns, and we have several brands of limb nadir matching products. So these we have all in mind. And the one question you could ask is, what would the user prefer? What would modelers prefer? Would you prefer one unified best multi-instrument tropospheric ozone dataset, or would you prefer that you better consider in your comparisons multiple single instrument based datasets and consider these more useful? And if you would choose for the latter option, then the question is, what additional information would you need to intercompare and analyze these datasets? Because then it's up to the modelers to understand all the differences between observations. Well, if you would have a unified tropospheric ozone dataset, you have left this to the people to do the observations. So that's, I think, the first question maybe to start with. Maybe some have some comments on this, and my suggestion would be that you can raise your hand, but I don't know if I will see our raised hands. Is that you just mention in the chat that you want to say something, and then I give you the word. Okay, I have a comment. The one that wrote that can say something.
Okay, I think that's me. Yeah, I think for the tropospheric ozone column data, it depends which question you're asking. If I remember the presentations today, the spatial distribution and the amounts seemed quite similar, but what gives me pause thinking, you know, one unified best data set is the fact that the trends were radically different across the different data sets. And I don't know how you would, you know, be able to get that down to a single data set, and what you would, you know, perhaps give people a false sense of confidence about what that best data set actually represents. So I think there's two parts of the question. There's just the spatial distribution and climatology, but the trends is a more difficult one.
Of course, the trends is really one of the aims, but it's not the only research question indeed. So there, I also see that Stephanie says, I agree, it depends on the research question. So maybe, can you comment on that? Stephanie? I cannot hear, so I tend to go on to the Paul Newman. You raised your hand.
Yeah, thanks, Mikhail. And this is I'm kind of jumping off where David his comment, and this refers to the also part of the best multi-instrument. And I was also struck by the divergence in trends. Most of these trends are not very long. So the ability of models to actually represent short trends is really hard, particularly a free-running model. It'll give you all sorts of different solutions, and if you're comparing it to a trend that has huge uncertainties, I don't think we're achieving a lot of science. But it strikes me that a lot of these trends that we see in the satellite data begin with differences in their year-to-year variability. So when I was looking at matched trends, I'd see some years that number of them would be high, another year a number of them would be low, but they didn't always match up. It seems to me that the satellite community has to figure out what they truly believe is correct in the satellite data and what they think is a little bit uncertainty. So it's a level of confidence within the satellite data systems themselves that there needs to be a better definition. So instead of trying to work too hard on trends, just try to figure out why you're on this. All the observations on one side of a mean line, or are they below one side of the mean line? I think that's where you really, so defining, and I saw it a few times, satellite observations versus tropospheric column or tropospheric amounts from ozone sondes. I think you really want to understand what you truly believe first before you start going off and trying to do trends, even trying to make sure that the satellites are doing the same annual cycle seems to me more important than actually getting a trend right. Trends always involve, you know, different forcings. As Paul just showed, you know, methane is a big driver here, NOx is a big driver, and so trying to interpret a short trend is really hard. But trying to understand an annual cycle is a much more tractable problem. And then just trying to understand why data are on one side of a mean line, the high side, or versus the low side. So take extreme years and see if the satellites can all duplicate the extreme years. So that's just a broad comment about trying to match up with models. I think the satellite folks need to define what they truly believe with 100% confidence and what they believe with maybe low confidence.
Yes, thank you, Paul. This is, I think, very interesting indeed, and this focus on the internal variabilities of the instruments and understanding of the different instruments and what in any way is needed. Also, if you want to unify and come to a unified data record, you also have to understand this. So maybe there are some additional comments on this, and also on this. What information would you need when you get different? Of course, you want to know about uncertainties of your data set, but maybe there are other specific needs for users that want to use different data sets. Dan?
Yeah, perhaps to respond to Paul's remark on comparing satellite data, I just wanted to add that this is one of the goals, of course, of TOAR II. And now that we have all these data sets available, do these more in-depth comparisons, not just of the trends, but also the smaller scale features. That's ongoing, so there's no answer from the community here. But I can already guarantee you with 100% certainty that we will never be 100% certain of the observations being correct in one way or the other. So having the experience in the stratospheric ozone community and Lotus, and many of the people here are also participating to this, there's always differences between observations that are unavoidable. So it's a matter of trying to get the best possible interpretation of the different data sets. And that's only possible by comparing many data sets to many data sets. And that's why it's so valuable to have different complementary techniques and different sensors. And this is really important if it's so hard to do the measurement.
One way could be what Carl said on this November issue, that he said, yeah, I see an extreme month, but nobody else has mentioned this. So that could be a way where you can really try to get to certain case studies for certain months, for certain regions. And if you can understand these and the differences, and if data sets can manage to get into agreement on these more extreme situations, then you can maybe get better trust in the internal variability. So the challenges, what challenges do you foresee is the last question, and that is that maybe it's that mainly on the instrument people and the retrieval people. So what are the challenges to really in this harmonization of data sets, or this understanding of differences between data sets? So I think one standing issue is always is these definitions of tropopauses, and what do you refine, and is these parameters are these sufficiently well defined? And we saw the importance of the averaging kernels. I was also struck by the comment that total ozone is not always the sum of all layers. There's also an enormous factor in the total column, which might be important. Stephanie, do you think you have a microphone now?
Let's try. Does it work now?
Yes.
Perfect. So I had some difficulties with Teams again. It blocked my complete audio and video. Okay, so regarding the tropopause heights, I mean, from the modeling world, you see that there's a lot of variation on day-by-day basis, which is probably not used at all when reconstructing any column values from satellite observations. So I also wonder how large the variation would be if you would actually use the actually daily variation of tropopause height.
Yes, That's maybe someone can comment on this.
Well, if no one comments, I know the lim-nadir matching products, they use daily tropopauses. The actual computation of the tropospheric column is done at a daily level, as far as I understood, and please correct me if I'm wrong. But at the daily level, the tropopause information is used, and then the final product is then aggregated in time and space to monthly 1 by 1 degrees. So if there is a tropopause in the final product, it's the monthly mean tropopause, but that's not the tropopause that was used to derive tropospheric column for all measurements during that month. That's for the lim-nadir matching products. For CCD, there is no tropopause. It's always a fixed pressure level, so it's not really a full tropospheric column. And for profile retrievals, you basically do whatever you like because you have the full profile. So a user can integrate up to whatever level they want. So there, the difficulty would be for CCI, the level 3 products at monthly mean level. Even though you have a profile, you don't have the daily profile anymore. So for this product, you are right. You cannot accommodate for a daily changing tropopause because you only have a monthly profile.
Maybe you could help the modelers by providing some daily information in your monthly files that they can better sample their model when comparing monthly means. You can think of additional information because the modelers have to sample preferably their model for the moments that the observations have been made.
Exactly. But thanks a lot for your explanations, Dan.
That's an interesting point on the sampling. I always wondered, what would you need? So would you need lat-long timestamps for every single 1 by 1 degree monthly bin? Are model people really sampling? When they do the comparison to data, do they really do all the effort to do the exact sampling as satellite? If it is useful, it will be definitely something interesting for our team to look into and find out whether we can provide this.
I mean, what I've been doing so far with GOME 2 data was trying to sample the overflight times to the local time zones in the model to match the overpassing of the satellite to get and then estimate the monthly mean profiles again in comparison with the satellite. Because if I take just all the data in the model, it doesn't match at all with what the satellite actually saw. And if there's some overflight information already easily available from the satellites, would already help. Else you have to really do all this geometrical calculations.
But that's for a model study that is on small scales, or is this like a long-term global study?
I mean, in this case, it was about bromine monoxide in the Arctics, for which I did these integrations.
Yeah, so someone else raised his hand, so maybe come in and help the discussion.
I just raised my hand.
Yes.
I just want to comment that most of or almost all of this information is available as soon as you go to the single measurements of the instruments, and it's just a question of effort if you would like to use this information or if you prefer to use the higher level products. But in principle, all this information is available from most of the instruments. And okay, if I comment already, I would also like to say that there is a SPARC or an APARC effort to unify the error reporting of satellite data, which of course is also important for assessing any biases or drifts between satellite data, and that's the tuner activity, which will hopefully go on. Yeah.
Thank you.
Thanks, Gabi. This is indeed correct. The level 2 data are available. CCI provides level 3 products where you lose this daily information because most products are monthly level, but the level 2 profiles used to build these level 3 are either publicly released or can be obtained by contacting the team. That being said, for some products, it's inherently impossible to. Yeah, no, that's all. You can get the information you need on the sampling.
Yeah, so that's also in the comments in the chat. It said that CCMi does ask groups to submit a tropospheric column, and I'm not sure what everyone does, but the hope is that they do use daily or sub-daily tropopause position when calculating the monthly average tropospheric column. So I think that's maybe an issue that can be discussed within the teams further. That what could be done on sampling for monthly mining products. Maybe we should go to the next slide. And the last slide for.
I see one question before Dave's comment. Michiel from Sullivan.
Oh, sorry, it does more frequency temporal sampling, each less than a day, over interest areas have benefits to modeling, especially for tropospheric ozone over small interest regions. Yeah, that's an important question. Which also will come along with these geostationary platforms. Of course. So is there, to add, that really depends on the research questions that you have as a modeler. Are you looking really at long-term trends, or are you looking at this case studies and events? Yeah, go ahead.
So if you're looking for certain processes which might be missing in your model to explain the observations or so, sub-daily sampling would actually be appreciated, because you cannot see, for example, the interaction of ozone with vegetation in the monthly means, at least not with respect to the photolysis cycle and so on.
Yes, so for the general cycle of ozone might be important if you could have information from models, from my observations, but that depends, of course, on what are the possibilities there to derive this. I would like to move on to the last point, and that is more on the priorities also for the team. On the question that we have posed here is, what do you think would be needed to increase the quality and usefulness of tropospheric ozone data as provided by Ozone CCI, and how could we further increase the use and visibility of these data sets? And then what action should the team prioritize? Is it really journal publications and associated data sets, and that we have the most impact? Is it through active support to international activities? And or is it through tailored websites, data portals, and user consultations, like the user workshop that we have today? Or is it all? What do you think is should be the priority for the ESA team? Or do you have other suggestions? Are we missing elements in our getting our data across in the community.
Hey, Michiel, if I may, this is Arno.
Yes, go ahead.
Well, to me, I'm more on the validation side, but in that respect, also a user of the data. But I still think that journal publications are a prerequisite within our community and also inspire the others. So usually to contribute to an assessment, you need a publication deadline, or you need to have published your data somewhere before. And then only then they are considered in the assessment. And then related to that, if more and more with publications, you publish the data with a separate DOI or something. So connected either to a specific data portal or just a DOI archive. But usually the data are much more findable when they're discussed in a publication and then connected to the publication either with the DII or with a reference online. So I think the first one is the prerequisite for the others as well, and is to me, I think, the prior motivation.
Okay, thank you. Yeah, I think that's probably correct to say. Indeed, for assessments, it's a prerequisite to have this referenced data sets. But still, for the teams, it's difficult to where do you prioritize? If you spend a lot of time on making your publication, then you have less time to help in international efforts or to work on data portals, etc. So of course it's the combinations, but it's difficulty sometimes to prioritize. Also, maybe the related question is that, do you think that the data sets of CCI are well available? And do we well?
Well, when it comes to this session on tropospheric ozone, the difficulty is perhaps that formally our tropospheric ozone data sets, a good number of them are not yet publicly released. So from the strict point of view, they are not available, but will soon be. So I don't know whether that impacts people's view on availability of our tropospheric ozone datasets. Tomorrow on the stratospheric ozone session, our datasets have been available for much longer. So that would be nice to hear from the community what the difficulties are to find our data.
Yes. So there's also comments that from Shuburi Wahid that I would greatly appreciate a monthly news bulletin that may inform us about recent publications, datasets, and workshops. So I think indeed that's always useful that you communicate on new elements, and as soon as the project has new datasets released, that this is communicated to users and participants, let's say, of this workshop. So yeah, it's always difficult to have such discussions online with people hesitating to step in. But
may I ask a question back to Mr. Shaduri? Whether I see the role maybe not with CCI to do this work, but there are a number of community initiatives. APARC, for instance, previously Spark, has a monthly or a few monthly newsletter, which really lists workshops for the community. Not data sets necessarily, And sometimes publications are, I think they have a list of publications, but on the website. So that could be a source of information, this APARC newsletter. But from our side, we don't have a lot of news every single month, of course, not news that is useful for the general user. Yeah, perhaps we can think about it, of doing it at a 6 monthly or every year or so scale. I'll write this down.
Yep, thanks, Dan. So, Irina, for interpretation of total ozone change, you need tropospheric ozone data here, and longer data sets, thus combined records are needed. Also, please participate in the Quadrennial Ozone Symposium. We will have a session on tropospheric ozone. That's very useful information, of course. A lot of people will be aware of this, that this quadrennial is upcoming in Boulder. Irina, would you like to comment on that further?
I can try. Can you hear me?
Yes.
Oh, okay, all right. Yeah, definitely. We have Quadrennial Ozone Symposium in Boulder this summer, July 15th through 19th. And the deadline actually coming up for the early bird registration, May 31st. So if you don't want or cannot come, in person, so sorry. But there is online version available, so you will be able to listen to all the presentation and ask questions. That's a very nice venue because you have discussions of both stratospheric ozone, tropospheric ozone, climate, all different kind of aspects of the ozone, and data sets, of course, and observational records. Sorry for bluntly advertising here.
No, I think it's very important. You have the right community here to address.
I don't know if somebody have not heard of it, so that's why I've typed the link to the webpage. And for the tropospheric ozone, we keep on saying that the Lotus will address the tropospheric ozone trends, but I think those, the data sets are the most important one. And so as long as we have coherent understanding of what's going on with tropospheric ozone, we can understand what's happening with total ozone and separate tropospheric ozone from stratospheric ozone trends, and then with the help of the models, look into the attributions, what's driving those changes. So all the data I needed, there's no really a thing saying like bad data, good data. That's what Dan was saying. We need all of the data, and while we're doing intercomparisons, then we might be able to sort things out. And we'll just push forward. I think it's an important topic. Thank you.
Yeah, thank you very much. Yeah, I think with the increasing number of tropospheric ozone products and increasing lengths of the records, we will be able to better and better to indeed use both products together, the total ozone records and the tropospheric ozone records, to better understand changes over time. That really will help in the coming years. I think we had a very nice first day of this workshop, and I think unless someone has some last thing he would like to bring in for this first day on tropospheric ozone, because tomorrow we have a day on stratospheric ozone, total ozone.
I'd like to thank my fellow collaborators in the CCI team and then the conveners of today, Martin, Michiel, to lead this day. And I agree with you. It was a very nice first day. So look forward to tomorrow.
Thank you very much. And I think, I don't know if you have a last word to say, Martin, but then we can close for the day.
I'm fine.
I'd like to see you back tomorrow.
Yeah, see you tomorrow.
Stratospheric ozone session.
See you tomorrow.
See you. Bye.
Bye.
Bye.